Our Milky Way galaxy is not just drifting aimlessly through space. It is being drawn toward an unknown gravitational force called the Great Attractor. This mysterious region, located about 150 to 250 million light-years away, exerts a pull on thousands of galaxies, including our own, causing them to move at high speeds toward this unseen mass. The Great Attractor resides in a region of space densely filled with cosmic dust, making it difficult for astronomers to observe directly. However, its gravitational influence is undeniable, creating what scientists call a dark flow of galaxies moving toward this hidden force. The exact nature of the Great Attractor is still unclear, but some theorists believe it could be the center of a vast supercluster, or perhaps a dense concentration of dark matter. Studying the Great Attractor helps scientists understand large-scale cosmic structures and the influence of hidden masses. This pull on our galaxy reminds us that the universe is far from static. It is a dynamic, interconnected web where even our home galaxy is constantly in motion, influenced by forces we are only beginning to comprehend. The Great Attractor, the cosmic force pulling our galaxy. Imagine the Milky Way drifting through space, surrounded by neighboring galaxies in the local group, yet all being pulled toward a gravitational source we can't fully see or understand. This mysterious entity, known as the Great Attractor, exerts a powerful force on thousands of galaxies, including our own, causing them to travel at incredible speeds toward an unknown destination. Located roughly 150 to 250 million light-years away in the direction of the constellation Centaurus, the Great Attractor challenges our understanding of cosmic forces and structures. The region where the Great Attractor resides is densely filled with cosmic dust, obscuring our view and making it challenging to study directly. Astronomers have observed its effects through the peculiar velocities of galaxies, which are moving in ways that can't be explained by the expansion of the universe alone. Unlike other regions that follow predictable paths set by cosmic expansion, galaxies in this area are drawn inward by a gravitational source that seems to defy conventional explanations. Theories about the Great Attractor range widely. Some scientists believe it could be the center of an enormous supercluster or an immense concentration of dark matter, forming a gravitational hub. Others suggest it could be part of a massive cosmic structure stretching even farther, one that includes the Great Attractor as just a segment of a much larger gravitational influence extending across hundreds of millions of light-years. For decades, astronomers have mapped the movement of galaxies and studied their velocities in detail to estimate the mass of the Great Attractor. These studies reveal a hidden structure of staggering proportions, potentially containing the equivalent mass of thousands of galaxies. This immense pull isn't just felt by our galaxy, it affects galaxies across the Laniakea supercluster, a structure that spans over 500 million light-years. Within Laniakea, galaxies follow pathways defined by the gravitational influence of dark matter and unseen structures, guided toward regions of higher mass. Advancements in technology, particularly through powerful observatories and advanced mapping techniques, have allowed scientists to peer slightly deeper into the dust-enshrouded area where the Great Attractor is located. Yet, its nature remains one of astronomy's greatest puzzles. Why is there such a concentrated pull in this region? What unseen forces are at play, and could they be remnants of ancient cosmic events? The Great Attractor reveals that even on vast cosmic scales, regions of intense gravity and invisible structures can dictate the movement of galaxies. It serves as a reminder that our understanding of gravity, dark matter, and the fabric of space itself is still evolving, with discoveries on the horizon that may challenge or redefine what we know about the universe. The Great Attractor reminds us that we are part of a cosmic journey, pulled by unseen forces toward destinations that lie beyond our current understanding. Exoplanets and the search for life beyond Earth. In recent decades, the discovery of thousands of exoplanets has opened a new frontier in the search for extraterrestrial life. An exoplanet, or extrasolar planet, is a planet that orbits a star outside our solar system. These planets vary widely, from gas giants larger than Jupiter to rocky worlds similar to Earth, each orbiting in unique environments that challenge our understanding of planetary formation and the potential for life. One of the most exciting aspects of exoplanet research is the possibility of discovering habitable worlds, planets that have conditions suitable for life as we know it. Astronomers focus on planets located in the habitable zone, a region around a star where temperatures are neither too hot nor too cold, allowing for liquid water to exist on the planet's surface. Finding such planets has become a major goal for missions like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, which have identified thousands of candidates, bringing us closer to answering the age-old question, are we alone in the universe? The study of exoplanets has led to the discovery of super-Earth's rocky planets larger than Earth, but smaller than Neptune. These worlds have become prime targets for habitability studies, as their size and mass may provide the right conditions for stable atmospheres and geological activity. In addition to super-Earths, scientists have discovered hot Jupiters, gas giants that orbit extremely close to their stars. The diversity of these planetary systems challenges the traditional models of planetary formation, as it reveals environments far different from our solar system. One of the most promising methods for studying exoplanets is spectroscopy, where scientists analyze the light that passes through a planet's atmosphere as it transits its star. By breaking down this light into its component wavelengths, researchers can identify the chemical signatures of various gases. Discoveries of water vapor, carbon dioxide, methane, and oxygen in exoplanet atmospheres would be highly significant, as these molecules are associated with life processes on Earth. The presence of both oxygen and methane, for example, could indicate biological activity, as these gases typically react with each other and are unlikely to coexist without a source. The James Webb Space Telescope, JWST, launched to continue exoplanet studies, has already provided unprecedented detail about planetary atmospheres and surface conditions. Future observatories, such as the European Space Agency's Ariel mission, aim to survey the atmospheres of hundreds of exoplanets, furthering our understanding of planetary diversity and potential habitability. With each discovery, we inch closer to identifying a world that might support life. Exoplanet research challenges us to think beyond our solar system, expanding our understanding of what constitutes a planet and what conditions might support life. These distant worlds, each with unique characteristics, offer a glimpse into the complexity and vastness of the cosmos. They remind us that life could exist in forms and environments beyond our imagination, waiting to be discovered as we continue to explore the stars. Dark matter and the universe's hidden Massachusetts. Dark matter is one of the greatest mysteries in modern physics, representing a type of matter that does not emit, absorb, or reflect light. Despite its invisibility, dark matter makes up about 27% of the universe, vastly outweighing ordinary baryonic matter, which comprises stars, planets, and all visible structures. Observations of galaxy rotations and the gravitational lensing of light reveal dark matter's presence, suggesting that it plays a critical role in holding galaxies together and shaping the cosmic web. The concept of dark matter emerged in the 1930s when astronomer Fritz Zwicky studied the Coma galaxy cluster and found that the galaxy's observed motions required far more mass than could be accounted for by visible matter alone. Decades later, Vera Rubin's research on galaxy rotation curves provided additional evidence. Rubin discovered that stars at the edges of galaxies orbit at unexpectedly high speeds, implying an unseen mass that extends beyond the visible edge of a galaxy. This missing mass phenomenon pointed directly to dark matter as the only viable explanation. While its existence is widely accepted, dark matter's true nature remains elusive. It does not interact with electromagnetic forces, meaning it doesn't emit, reflect, or absorb light, making it incredibly difficult to detect directly. Scientists hypothesize that dark matter could consist of unknown particles, such as WIMPs, weakly interacting massive particles, or actions. WIMPs, if they exist, would interact with regular matter through gravity and possibly the weak nuclear force, while actions are hypothetical particles with an extremely low mass that could account for dark matter in significant quantities. Efforts to directly detect dark matter are ongoing, with experiments deep underground, in laboratories shielded from cosmic rays, and even aboard the International Space Station. Instruments like the Large Underground Xenon (LUX) detector, located in a former gold mine in South Dakota, are designed to capture faint interactions between dark matter particles and ordinary matter. So far, these experiments have not provided definitive evidence, but they are constantly improving in sensitivity, pushing the limits of what can be detected. The influence of dark matter is not limited to individual galaxies. On a cosmic scale, dark matter forms the backbone of the universe's large-scale structure. Computer simulations of the universe's formation, such as the Millennium simulation, show that dark matter clumps together under gravity, creating a vast cosmic web that acts as scaffolding for ordinary matter. This web-like structure determines where galaxies form and how they cluster together, giving rise to the universe's intricate and interconnected structure. Understanding dark matter is crucial for unraveling the mysteries of the universe's formation, structure, and ultimate fate. It represents a fundamental component of reality that remains hidden, influencing galaxies, stars, and the cosmos in ways that we can only infer. Dark matter challenges our understanding of matter and forces, suggesting that much of the universe is governed by invisible influences that shape everything from the smallest particles to the largest galaxy clusters. The cosmic microwave background, a glimpse into the early universe. The cosmic microwave background, CMB, is a faint glow of radiation that fills the universe, providing a snapshot of the cosmos as it appeared around 380,000 years after the Big Bang. Discovered by accident in 1965 by radio astronomers Arno Penzias and Robert Wilson, the CMB is one of the strongest pieces of evidence supporting the Big Bang theory. It represents the moment when the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms, allowing photons to travel freely for the first time. The study of the CMB has revolutionized cosmology, allowing scientists to learn about the conditions of the early universe with remarkable precision. The temperature of the CMB is nearly uniform across the sky, at about 2.7 Kelvin, or just above absolute zero. However, tiny fluctuations, known as anisotropies, reveal slight variations in temperature that correspond to regions of slightly higher or lower density. These fluctuations were the seeds of galaxies and cosmic structures, as gravity amplified them over billions of years, leading to the formation of stars, galaxies, and clusters. Observatories such as the Wilkinson Microwave Anisotropy Probe, MAP, and the Planck satellite have mapped these fluctuations in extraordinary detail, providing insights into the universe's age, composition, and rate of expansion. The data from the CMB has allowed scientists to refine measurements of key cosmological parameters, such as the density of dark matter, the amount of dark energy, and the Hubble constant, which describes the universe's rate of expansion. One of the most profound aspects of the CMB is that it offers a glimpse into the universe's infancy, revealing conditions from a time when the universe was opaque and filled with hot plasma. Before the CMB was emitted, photons were constantly scattered by free electrons, creating a fog that prevented light from traveling freely. This epoch is known as the recombination era because it marks the period when electrons combined with protons to form neutral hydrogen, allowing light to escape and create the CMB. This ancient light has traveled across the universe for over 13 billion years, reaching us as a faint, pervasive glow in the microwave spectrum. The study of the CMB has also provided evidence for cosmic inflation, a rapid expansion that occurred fractions of a second after the Big Bang. This inflationary period stretched quantum fluctuations to cosmic scales, creating the initial density variations observed in the CMB. The theory of inflation explains why the CMB appears nearly uniform, as regions that were once in contact expanded beyond each other's reach, creating the large-scale homogeneity we see today. The cosmic microwave background is a relic of the universe's earliest moments, a distant echo of the Big Bang that carries information about the forces and events that shape the cosmos. It reminds us that even in the silence of space, there are ancient signals that speak to the origins of everything we know, connecting us to the birth of the universe itself. The fate of the universe, Big Freeze, Big Crunch, and Big Rip. As scientists continue to study dark energy and the universe's expansion, the question of the cosmos' ultimate fate becomes increasingly significant. There are three primary scenarios for the end of the universe: the Big Freeze, the Big Crunch, and the Big Rip. Each scenario is based on different properties of dark energy and the behavior of cosmic expansion over time. The Big Freeze, also known as heat death, is the most widely accepted scenario given current observations. In this scenario, the universe continues to expand indefinitely, causing galaxies to drift further apart and the overall density of matter and energy to decrease. As the universe ages, stars will exhaust their nuclear fuel, and new stars will cease to form, leaving behind a universe filled with cold, dead stars, white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will decay or be absorbed by black holes, leading to a universe that is cold, dark, and nearly empty at true cosmic silence. In the Big Crunch scenario, the expansion of the universe eventually reverses, causing galaxies to collapse back together. This theory suggests that gravity could ultimately overpower dark energy, halting expansion and triggering a cosmic contraction. As the universe shrinks, galaxies would merge, temperatures would rise, and all matter would eventually collapse into a singularity, a point of infinite density. Some theorists suggest that this collapse could lead to a new Big Bang, in a cyclic model where the universe undergoes infinite cycles of expansion and contraction. The Big Rip, on the other hand, is a more extreme and dramatic possibility. If dark energy's influence increases over time, it could cause the expansion of the universe to accelerate to the point where galaxies, stars, and even atoms are torn apart. In this scenario, known as phantom energy, the force of dark energy would grow stronger with time, overcoming gravity and all other fundamental forces. Eventually, galaxies would be ripped apart, followed by solar systems, planets, and even individual atoms. The fabric of space-time itself would be torn asunder, leaving behind nothing but isolated particles and a final, destructive end. The ultimate fate of the universe depends on the properties of dark energy, which remain one of the biggest mysteries in cosmology. Observations of distant supernovae and galaxy distributions continue to provide clues about the nature of dark energy, but its exact behavior over cosmic timescales is still uncertain. Understanding the universe's fate not only deepens our comprehension of cosmic forces, but also raises philosophical questions about the nature of time, existence, and permanence. The possible endings of the universe challenge us to consider the impermanence of everything in existence. Whether the universe fades into a dark, empty void, collapses in a fiery end, or tears itself apart, these scenarios reveal the transient nature of cosmic structures. They remind us that even the stars, galaxies, and forces that seem timeless are subject to the vast, ongoing processes of creation and destruction that define the universe. Gravitational waves, ripples in the fabric of space-time. Gravitational waves are ripples in space-time caused by massive objects accelerating, such as black holes or neutron stars spiraling toward one another. Predicted by Einstein's theory of general relativity in 1915, these waves remained undetected for a century due to their incredibly faint nature. It wasn't until 2015 that the LIGO Laser Interferometer Gravitational Wave Observatory collaboration successfully detected gravitational waves from a pair of merging black holes. This monumental discovery opened a new era of gravitational wave astronomy, offering a novel way to observe some of the most powerful events in the universe. Gravitational waves travel at the speed of light, stretching and compressing space as they move through it. Unlike light, which can be blocked or scattered, gravitational waves pass through virtually anything, allowing them to carry information from the most extreme and hidden regions of the cosmos. Observing gravitational waves enables scientists to listen to the universe, capturing signals from events that are invisible to traditional telescopes, such as black hole mergers and neutron star collisions. The detection of gravitational waves has already led to numerous groundbreaking discoveries. For instance, in 2017, LIGO and Virgo observatories detected waves from a neutron star collision. This event, dubbed GU 17817, not only confirmed the existence of neutron star mergers, but also led to the detection of a corresponding gamma-ray burst, providing a direct link between gravitational waves and electromagnetic radiation. This multi-messenger observation allowed astronomers to study the same cosmic event through both gravitational and light signals, yielding insights into the production of heavy elements like gold and platinum. Gravitational waves have also revealed details about black holes that were previously unknown. Observing black hole mergers has shown that these enigmatic objects can form in pairs and merge, creating new, larger black holes. These observations suggest that black hole binaries are more common than once thought, potentially reshaping our understanding of stellar evolution and the end stages of massive stars. Each new detection adds to our understanding of how black holes form, interact, and shape their surroundings. The future of gravitational wave astronomy is promising, with upcoming observatories like LISA, Laser Interferometer Space Antenna, set to detect waves in space. Unlike ground-based detectors like LIGO, LISA will orbit the Sun, allowing it to detect lower-frequency gravitational waves from sources such as supermassive black holes or even potential signals from the early universe. These advancements could reveal even more about the universe's hidden dynamics, offering a detailed look at how gravity influences cosmic structures over billions of years. Gravitational waves remind us that the universe is far more than what we can see. They reveal a cosmos where space itself vibrates, carrying messages from distant, violent events across unimaginable distances. As we continue to develop tools to detect these faint signals, we gain access to a universe previously hidden, expanding our understanding of how massive objects interact and shape the fabric of reality. The arrow of time. Why does time move forward? Time, as we experience it, flows in one direction from the past to the future. This arrow of time is a fundamental aspect of reality, yet its origins and nature are deeply tied to the laws of thermodynamics and the concept of entropy. According to the second law of thermodynamics, in a closed system, entropy or disorder tends to increase over time. This principle is why we observe time moving forward, as processes naturally progress from states of lower entropy, order, to higher entropy, disorder. The arrow of time is observable in countless everyday processes, a cup shattering, an egg cracking, or a drop of ink diffusing in water. These events are irreversible, they only move in one direction. This irreversibility is a key characteristic of macroscopic events governed by thermodynamics, contrasting with the fundamental laws of physics, which are time-symmetric. In theory, at the particle level, processes could run backward, but in practice, the macroscopic world adheres strictly to the forward flow dictated by entropy. Physicists and philosophers have long debated whether time's arrow is an intrinsic property of the universe or a result of human perception. Some suggest that time might not have a single direction across the entire universe. In regions with different physical conditions, or even in potential alternate universes, time could behave differently. This speculation ties into theories of the multiverse, where different versions of reality might experience unique temporal flows. Understanding time's arrow has implications for fields as varied as cosmology, thermodynamics, and information theory. The irreversible nature of time is essential for processes like memory formation, biological growth, and the evolution of complex systems. In the realm of black holes, for example, the concept of entropy leads to profound paradoxes, as information seems to disappear beyond the event horizon. This paradox has driven some theorists to propose that information is preserved on a black hole's surface, suggesting that time and entropy may behave differently under extreme conditions. The arrow of time is a fundamental aspect of human experience, shaping how we perceive reality and construct narratives of past, present, and future. It invites us to question whether time is an illusion or a fundamental aspect of the universe. Ultimately, the study of time's arrow forces us to confront the mysteries of existence, entropy, and the vast, irreversible journey that defines our place in the cosmos. The search for extraterrestrial life. Are we alone? The search for extraterrestrial life is one of humanity's most enduring quests, driven by the fundamental question of whether we are alone in the universe. This pursuit spans disciplines from biology to astrophysics, employing tools and techniques that range from studying microbes in extreme Earth environments to scanning distant planets for biosignatures. Each discovery and hypothesis brings us closer to answering one of the most profound questions about our place in the cosmos. One of the primary methods for finding extraterrestrial life is the study of exoplanets, specifically those located in the habitable zones of their stars. These zones, often referred to as the Goldilocks zones, are regions where conditions may allow for liquid water to exist on a planet's surface. Since water is essential for life as we know it, planets in these zones are prime candidates in the search for life. Recent discoveries of Earth-like exoplanets around stars like Proxima Centauri and in the TRAPPIST-1 system have fueled excitement about the potential for habitable worlds beyond our solar system. Astrobiologists are particularly interested in detecting biosignatures, indicators of biological processes on distant planets. These could include gases such as oxygen, methane, or nitrous oxide, which are typically produced by living organisms. Instruments like the James Webb Space Telescope, JWST, and upcoming missions like Ariel are designed to analyze the atmospheres of exoplanets, searching for these chemical markers. The simultaneous presence of oxygen and methane, for instance, would be a strong biosignature, as these gases would ordinarily react and disappear from an atmosphere without a continuous source, such as life. Closer to home, the search for life focuses on the moons of the outer planets, particularly Europa, Enceladus, and Titan. Europa, one of Jupiter's moons, has a subsurface ocean beneath its icy crust, where tidal heating from Jupiter's gravity creates conditions that may support microbial life. Similarly, Enceladus, a moon of Saturn, ejects water plumes from a global ocean, containing organic compounds that hint at the potential for life. Titan, with its lakes of liquid methane and complex organic chemistry, offers a unique environment where life could exist in forms radically different from those on Earth. The search for extraterrestrial life also extends to listening for signals from intelligent civilizations. The search for extraterrestrial intelligence, SETI, uses radio telescopes to scan the skies for signals that might indicate advanced civilizations attempting to communicate. The discovery of even a single signal from an extraterrestrial source would be groundbreaking, offering direct proof that intelligent life exists beyond Earth. Despite decades of searching, no confirmed signals have been detected, but the vastness of the universe leaves open the possibility that intelligent life could exist on planets orbiting distant stars. The search for life challenges our understanding of biology, chemistry, and the conditions necessary for life to thrive. It forces us to expand our definitions of habitability, considering environments once thought too extreme or alien for life to exist. From the depths of Earth's oceans to the icy moons of the outer solar system, life has proven remarkably resilient and adaptable, leading scientists to believe that it may emerge in a variety of forms across the cosmos. Whether life exists beyond Earth remains an open question, but each discovery brings us closer to understanding our cosmic neighbors. The search for extraterrestrial life reminds us that we are part of a vast, interconnected universe, filled with possibilities and mysteries waiting to be uncovered. It invites us to ponder the profound implications of finding or not finding other forms of life in the cosmos, and what it would mean for humanity's place in the grand tapestry of existence. The multiverse theory, infinite realities beyond our own. The multiverse theory suggests that our universe may be just one of countless others, each with its own physical laws, constants, and potentially even dimensions. This idea challenges our perception of reality, proposing that beyond our observable cosmos lies a vast expanse of universes, each following its own unique set of rules. These parallel universes could vary slightly from our own, or be radically different, with entirely new physical properties and forms of matter. Another version of the multiverse arises from cosmic inflation theory. In the first fractions of a second after the Big Bang, the universe expanded at an incomprehensible rate, creating bubble universes within a larger multiverse. Each of these bubbles could contain a universe with different physical laws and constants. This theory suggests that some universes may not even support structures like galaxies or atoms, while others could contain entirely different forms of matter, forces, or dimensions. The multiverse also finds support in string theory, which proposes that fundamental particles are not points but rather tiny, vibrating strings. String theory suggests that there could be additional spatial dimensions beyond the familiar three, and that universes might exist in these hidden dimensions, separated from our own by distances beyond our perception. These hidden dimensions could harbor realities that exist parallel to ours but remain fundamentally inaccessible. While the multiverse theory remains speculative, it has profound implications for our understanding of reality. If other universes exist, then the fine-tuning of our own universe, the precise balance of forces and constants that allows for life may not be unique. Instead, we might simply inhabit one of the universes where conditions are suitable for complexity and consciousness. This idea is often referred to as the anthropic principle, suggesting that the universe's properties align with our existence because we are here to observe them. The multiverse theory challenges us to rethink the boundaries of existence, suggesting that what we perceive as the universe may be just a fragment of a far larger, infinitely complex reality. It raises questions about the nature of existence, free will, and the limits of human understanding. If there truly are infinite universes, then every possibility exists somewhere, making the multiverse a boundless landscape of realities, each shaped by different events, forces, and possibilities. While the multiverse theory remains beyond our observational reach, advancements in physics, particularly in quantum mechanics and cosmology, continue to inspire questions about the nature of reality. The idea of a multiverse reminds us that our understanding of existence is still limited, and that the cosmos may hold realms beyond our wildest imagination, where anything that can happen does happen, somewhere in an endless array of possibilities. Neutrinos, the ghost particles of the universe. Neutrinos are subatomic particles that are often referred to as ghost particles due to their elusive nature. They are incredibly difficult to detect because they interact only weakly with matter, allowing them to pass through almost any material without being absorbed or deflected. Every second, trillions of neutrinos pass through your body, originating from sources like the sun, cosmic rays, and even supernovae, yet they leave no trace. Neutrinos were first theorized in the 1930s by physicist Wolfgang Pauli to explain the missing energy observed in beta decay, a type of radioactive decay where particles seem to disappear without accounting for all the energy. Neutrinos were later detected in 1956, confirming their existence and marking a new chapter in particle physics. Today, neutrinos are recognized as fundamental particles that play a crucial role in understanding the universe's most energetic and violent processes. The Sun is a major source of neutrinos, producing them through nuclear fusion in its core. Studying solar neutrinos has helped scientists understand the processes that power stars, while also revealing the challenges of detecting these elusive particles. Neutrino observatories, such as the Super Kamiokande in Japan and the Ice Cube Neutrino Observatory in Antarctica, are designed to capture these ghostly particles as they pass through detectors buried deep underground or in ice. These observatories rely on detecting the rare interactions between neutrinos and atomic nuclei, which produce faint flashes of light. One of the most significant discoveries involving neutrinos came from a supernova in 1987, known as SN 1987A. When this supernova exploded, a burst of neutrinos reached Earth, providing a first-hand glimpse into the death of a massive star. The neutrinos from SN 1987 arrived before the visible light from the explosion. As neutrinos escape the core of a supernova faster than photons can. This observation confirmed that neutrinos play a critical role in the life cycles of stars, carrying away energy and contributing to the supernova mechanism. Neutrinos are also key to understanding the early universe. It is believed that relic neutrinos, also known as the cosmic neutrino background, permeate the cosmos, providing clues about conditions just seconds after the Big Bang. These neutrinos are incredibly low energy and nearly impossible to detect, but if studied, they could reveal fundamental insights into the universe's infancy. Neutrinos remind us that the universe is filled with particles and forces beyond our immediate perception. Their ghostly presence connects us to the processes that power stars and shape galaxies, offering a window into both the smallest particles and the most massive cosmic events. The study of neutrinos expands our understanding of particle physics, cosmology, and the fundamental workings of the universe. The Kardashev scale, measuring civilizations by energy use. The Kardashev scale is a theoretical framework proposed by Soviet astronomer Nikolai Kardashev in 1964 to classify civilizations based on their energy consumption. The scale consists of three primary types, Type I, Type II, and Type III, each representing a civilization's ability to harness and control energy on increasingly larger scales. Although originally intended to explore the potential of advanced extraterrestrial civilizations, the Kardashev scale has become a tool for understanding humanity's future technological potential. Type I civilizations, often referred to as planetary civilizations, have the ability to utilize all available energy on their home planet. This includes solar, geothermal, wind, and other renewable energy sources, as well as the full exploitation of fossil fuels. By Kardashev's definitions, humanity is not yet a Type I civilization, as we still rely heavily on fossil fuels and have yet to harness the full potential of renewable energy sources. Some estimates suggest that humanity could reach Type I status within the next few centuries if technological progress and energy consumption continue to grow. A Type I civilization, or a stellar civilization, is capable of harnessing the energy output of an entire star. This level of advancement would require monumental engineering feats, such as building a Dyson sphere, a hypothetical structure that surrounds a star and captures its energy output. A Type I civilization could use this energy to power space travel, develop advanced artificial intelligence, and create habitats for sustaining large populations. The leap to Type I is immense, as it would involve mastering energy on a scale far beyond what we can currently conceive. Type I civilizations, or galactic civilizations, have the ability to control energy on the scale of an entire galaxy. This includes harnessing the energy of billions of stars, as well as potentially tapping into phenomena like black holes or dark matter. A civilization of this level would be virtually omnipotent within its galaxy. With the technology to travel across vast distances, manipulate stars, and explore multiple star systems with ease, Type I civilizations would be capable of feats that, to us, seem indistinguishable from magic. Extensions of the Kardashev scale have been proposed to account for even more advanced civilizations, such as Type IV and Type V. These hypothetical civilizations would control the energy of multiple galaxies, or even the entire universe, respectively. Some theories even suggest the possibility of a Type O civilization, one that manipulates energy and information on a multiversal scale, shaping the fundamental laws of physics themselves. The Kardashev scale reminds us of humanity's potential and the vastness of technological progress. It challenges us to think beyond our immediate concerns, envisioning a future where we harness energy on cosmic scales and explore the universe as a collective species. Each step on the Kardashev scale represents a profound leap in capability, inviting us to imagine the possibilities and responsibilities of such advancement. The Fermi paradox. Where are all the aliens? The Fermi paradox highlights a puzzling question, given the vastness of the universe and the high probability of habitable planets. Why haven't we encountered any signs of intelligent extraterrestrial life? Named after physicist Enrico Fermi, this paradox contrasts the statistical likelihood of alien civilizations with the lack of observable evidence for their existence, sparking debate and countless theories about the nature of life in the cosmos. Our galaxy alone contains hundreds of billions of stars, many of which are orbited by planets. Estimates suggest that even if a tiny fraction of these planets harbored life, the galaxy could be home to millions of civilizations. With such a vast number of potential worlds, one might expect that at least some alien civilizations would have developed advanced technology, perhaps even reaching a Kardashev Type I or III level, and that their presence would be detectable across interstellar distances. Several hypotheses have been proposed to explain the Fermi paradox. One idea, known as the rare Earth hypothesis, suggests that while microbial life may be common, complex, intelligent life is exceedingly rare due to the unique combination of factors that allowed it to develop on Earth. These factors include Earth's stable climate, a large moon that stabilizes its tilt, and Jupiter's gravitational influence, which deflects potentially catastrophic asteroids. Another possibility is that advanced civilizations exist but avoid contact, a concept known as the zoo hypothesis. According to this theory, Earth might be part of a galactic preserve, where extraterrestrial civilizations observe us from a distance without interfering, much like humans might observe animals in the wild. This idea suggests that intelligent civilizations adhere to a form of non-interference, allowing species to evolve without external influence. Alternatively, some theorists propose that technological civilizations may have short lifespans due to self-destruction. The Great Filter hypothesis posits that there is a universal bottleneck that prevents civilizations from reaching advanced stages. This could occur at any point in a civilization's development, either before intelligent life evolves, before it achieves interstellar travel, or even after it reaches technological maturity but faces challenges like resource depletion or warfare. Another explanation is that alien civilizations may exist in forms or scales that are unrecognizable to us. Advanced beings might operate on scales beyond human perception, such as in digital realms, or be composed of non-carbon-based chemistry that eludes our detection methods. Life might also communicate in ways we cannot detect, or exist in places we have yet to explore, such as beneath the surfaces of moons or on rogue planets adrift in interstellar space. The Fermi paradox remains one of the most thought-provoking questions in science, touching on issues of evolution, technology, and the future of humanity. It reminds us that while we search for signs of other civilizations, we are simultaneously probing the boundaries of our own understanding. Whether life exists elsewhere or humanity is alone, the Fermi paradox forces us to contemplate our place in a potentially vast and silent cosmos. The Higgs field and the origin of mass. The Higgs field is a fundamental energy field that permeates the entire universe, endowing particles with mass through interactions with its associated particle, the Higgs boson. Named after physicist Peter Higgs, the field was theorized in the 1960s to explain why some particles, like protons and neutrons, have mass while others, like photons, remain massless. The discovery of the Higgs boson in 2012 at CERN's Large Hadron Collider confirmed the existence of this field, completing the standard model of particle physics. The Higgs field operates through a mechanism that can be likened to a cosmic molasses, providing resistance to particles that move through it. When particles interact with the Higgs field, they acquire mass. Those that interact more strongly gain more mass, while those that interact weakly or not at all, such as photons, remain massless. This interaction with the Higgs field is what gives particles the property of inertia, making it harder for them to change speed or direction. The discovery of the Higgs boson was a monumental achievement, as it confirmed a critical missing piece in our understanding of the universe. Without the Higgs field, fundamental particles would have no mass, and atoms, stars, planets, and life as we know it would not exist. The discovery has led to further questions, such as why the Higgs field has the specific properties it does, and whether similar fields might exist in other realms of physics. Studying the Higgs field also has implications for cosmology and the early universe. Shortly after the Big Bang, the universe was in a state of symmetry, with particles moving freely without mass. When the Higgs field activated, or condensed, it broke this symmetry, causing particles to acquire mass and leading to the formation of matter. This symmetry-breaking event allowed the universe to cool and form complex structures, setting the stage for the formation of galaxies and stars. The Higgs field invites us to explore the fabric of reality itself, challenging us to think about what properties are necessary for existence. It represents one of the universe's most fundamental forces, acting invisibly yet shaping everything we observe. The discovery of the Higgs boson not only validated decades of theoretical work, but also opened new doors to questions about the nature of mass, symmetry, and the underlying forces that govern the cosmos. Hawking radiation and the fate of black holes. Hawking radiation is a theoretical prediction by physicist Stephen Hawking, suggesting that black holes are not entirely black but emit a faint radiation due to quantum effects near their event horizons. This radiation causes black holes to lose mass over time, leading to the possibility that they could eventually evaporate and disappear. Hawking's theory revolutionized our understanding of black holes, challenging the view that they are permanent, inescapable cosmic sinks. According to quantum mechanics, the vacuum of space is not truly empty, but filled with pairs of virtual particles that momentarily pop into existence and annihilate each other. Near a black hole's event horizon, one particle of a virtual pair may fall into the black hole, while the other escapes, resulting in a net loss of mass for the black hole. This process, known as Hawking radiation, implies that black holes gradually lose energy and shrink, emitting radiation in the process. The rate of Hawking radiation is incredibly slow for large black holes, making it nearly impossible to observe directly. However, for smaller black holes, such as those that might have formed in the early universe, primordial black holes, the process could be faster. As a black hole loses mass, its temperature increases, causing it to emit radiation more intensely until it reaches a final burst, potentially releasing a powerful burst of energy as it evaporates. Hawking radiation has profound implications for the nature of information and the principles of quantum mechanics. One of the most debated issues is the information paradox, which questions whether information about the matter that falls into a black hole is lost forever when the black hole evaporates. According to quantum mechanics, information should be conserved. Yet Hawking's theory suggests that information could be irretrievably lost within black holes, creating a tension between quantum mechanics and general relativity. The study of Hawking radiation has led to ideas about holographic theories, where all information within a volume of space could be stored on a lower dimensional boundary. This concept has influenced theoretical physics, suggesting that the universe itself might operate as a hologram, where information about three-dimensional objects is encoded on two-dimensional surfaces. These ideas continue to inspire new approaches to understanding gravity, quantum mechanics, and the nature of space-time. Hawking radiation reminds us that even the most mysterious and powerful objects in the universe are governed by the principles of quantum mechanics. It challenges our understanding of reality, suggesting that black holes are not eternal prisons but dynamic entities that evolve over time. As scientists work to reconcile quantum mechanics with general relativity, Hawking's insights continue to shape our understanding of the universe's most extreme phenomena. Cosmic strings and the fabric of space-time. Cosmic strings are hypothetical, one-dimensional defects in space-time that may have formed in the early universe during phase transitions, similar to the way cracks form in ice as it freezes. These strings, predicted by certain grand unified theories, would be extremely thin but incredibly dense, with a single cosmic string potentially extending across the universe while having a mass equivalent to a large mountain or even a planet. If cosmic strings exist, they would have significant gravitational effects, distorting space-time around them. As they move, they could create gravitational waves, potentially leaving imprints on the cosmic microwave background or creating observable phenomena such as gravitational lensing. Detecting these signatures could provide insights into the early universe and the forces that shaped it, offering evidence for theories of cosmic inflation and the unification of fundamental forces. Cosmic strings might also provide clues about dark matter and dark energy. Since they would interact primarily through gravity, cosmic strings could have influenced the distribution of matter in the early universe, helping to seed the formation of galaxies and clusters. If they stretch across large distances, they might even connect different regions of the universe, acting as cosmic highways that shape the structure of the cosmos. The study of cosmic strings is linked to efforts to understand the underlying structure of space-time and the potential existence of higher dimensions. Some theories suggest that cosmic strings could be linked to branes or multidimensional surfaces predicted by string theory. These branes might intersect or interact with our universe, creating localized phenomena that we perceive as cosmic strings. If such structures exist, they could provide a tangible link between quantum physics and cosmology, bridging the gap between the smallest and largest scales. While cosmic strings remain theoretical, their possible existence invites us to rethink the nature of space-time, gravity, and the forces that shaped the universe's early evolution. They remind us that the universe's fabric may contain hidden structures, relics from a time when the universe was governed by conditions vastly different from those we observe today. The search for cosmic strings represents the frontier of theoretical physics, where the cosmos' deepest secrets may lie hidden in the structure of space itself. White holes, theoretical opposites of black holes. White holes are hypothetical objects predicted by the same equations that describe black holes, yet they have opposite properties. While black holes pull in everything, allowing nothing to escape beyond the event horizon, white holes are theorized to expel matter and energy, allowing nothing to enter. A white hole's event horizon would function as a boundary from which matter and radiation can escape, but nothing could cross it from the outside. The concept of white holes stems from the mathematics of general relativity, specifically the solutions to Einstein's field equations that describe extreme gravitational phenomena. In a black hole, matter collapses to a singularity, a point of infinite density, creating an inescapable gravitational pull. The equations, however, also allow for a hypothetical time-reversed version of this collapse, resulting in a white hole where matter is expelled rather than drawn in. White holes remain speculative, as there has been no observational evidence of their existence. However, some theories suggest that white holes could be connected to black holes through wormholes, forming a structure known as an Einstein-Rosen bridge. In such a configuration, matter that falls into a black hole could, in theory, emerge from a white hole in another region of space-time, or even in a different universe. This idea connects to the concept of wormholes as potential shortcuts through space, though the stability of such structures remains highly uncertain. One radical theory proposes that the Big Bang itself might have been a white hole. In this view, the observable universe could be the result of matter, an energy emerging from a singularity in the distant past. This interpretation aligns with the concept of a white hole expelling matter, as the early universe experienced rapid expansion and the release of vast amounts of energy. While highly speculative, this theory provides an intriguing perspective on the origin of the universe, suggesting that the beginning of time could be associated with a white hole's expulsion of matter. Another possible role for white holes is in solving the black hole information paradox, which questions whether information that falls into a black hole is truly lost when the black hole evaporates. If black holes eventually transform into white holes, they might expel the information they had previously absorbed, preserving the principle of information conservation in quantum mechanics. However, this remains a contentious topic in theoretical physics, with various competing ideas and no definitive answer. White holes challenge our understanding of space, time, and gravity, representing a realm of physics that remains largely unexplored. They remind us that the universe's underlying equations allow for strange, counterintuitive phenomena that defy our everyday experiences. Whether white holes exist or are merely mathematical constructs, they expand our imagination, inviting us to consider realms of reality that lie beyond our current reach. Quasars, the cosmic beacons of the early universe. Quasars are incredibly bright objects located in the centers of distant galaxies, powered by supermassive black holes that actively consume surrounding material. As matter falls toward the black hole, it forms an accretion disk of intensely hot gas, which emits immense amounts of energy across the electromagnetic spectrum, from radio waves to gamma rays. Quasars are among the most luminous objects in the universe, capable of outshining entire galaxies and serving as cosmic beacons that illuminate the distant reaches of space. Discovered in the 1960s, quasars initially baffled astronomers, as their light appeared to come from objects billions of light-years away. This realization led to the understanding that quasars represent a stage in galactic evolution, occurring primarily in the early universe, when galaxies were more active and black holes were rapidly growing. Studying quasars allows scientists to glimpse the conditions of the early cosmos, providing insights into the formation of galaxies and the growth of supermassive black holes. Quasars are not only extraordinary for their brightness but also for the speed at which they can eject matter. Jets of particles are often emitted perpendicular to the accretion disk, propelled by the black hole's intense magnetic fields. These jets can travel at nearly the speed of light, extending across thousands or even millions of light-years, and influencing the surrounding intergalactic environment. The energy from these jets can prevent new stars from forming in the galaxy, shaping its evolution over billions of years. Quasars also play a key role in mapping the structure of the universe. Since they are visible at extreme distances, they act as cosmic lighthouses, illuminating intergalactic gas clouds and revealing the large-scale structure of the cosmos. By analyzing the absorption lines in the light from quasars, astronomers can study the distribution of matter between galaxies and the composition of the early universe. This information helps scientists understand how matter was distributed shortly after the Big Bang and how it evolved into the galaxies and clusters we see today. The study of quasars reveals a dynamic, turbulent universe, where the formation and growth of black holes drive galactic evolution. Quasars remind us that galaxies are not static, they undergo phases of intense activity and transformation. Through the study of these luminous objects, we gain insights into the origins and life cycles of galaxies, black holes, and the structures that make up the universe. Pulsars and magnetars, the universe's extreme stars. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. Discovered in 1967 by astronomer Jocelyn Bell Burnell, Pulsars are the remnants of massive stars that exploded in supernovae, leaving behind incredibly dense cores that spin at astonishing speeds. These beams sweep across space like lighthouse beams, and when they align with Earth, they create a pulsing effect, hence the name pulsar. The rotation rates of pulsars can be extraordinary, with some spinning hundreds of times per second. These fast-spinning pulsars, known as millisecond pulsars, gain their speed by accreting matter from a companion star, which transfers angular momentum and accelerates the neutron star's rotation. Millisecond pulsars are among the most stable natural clocks in the universe, with precise timing that rivals atomic clocks. This stability makes them invaluable tools for testing the theory of general relativity and studying gravitational waves. One of the most fascinating aspects of pulsars is their intense magnetic fields, which can be trillions of times stronger than Earth's magnetic field. These magnetic fields generate powerful electric fields, accelerating particles and creating radiation that escapes along the magnetic poles. This radiation can be detected as radio waves, X-rays, or even gamma rays, depending on the pulsar's energy and rotation speed. Magnetars are a rare and extreme type of neutron star, with magnetic fields even stronger than those of typical pulsars, reaching up to a quadrillion, 10-15 times the strength of Earth's magnetic field. These immense magnetic fields can cause starquakes on the magnetar's surface, releasing intense bursts of X-rays and gamma rays. Magnetars are thought to be the source of some of the brightest gamma ray bursts observed in the Milky Way, with energy so extreme that they can affect nearby satellites and ionize Earth's atmosphere. Pulsars and magnetars are key to understanding the life cycles of stars and the behavior of matter under extreme conditions. They are laboratories of high-energy physics, where particles and fields interact in ways that cannot be reproduced on Earth. Studying these objects provides insights into the nature of neutron stars, the role of magnetic fields in stellar evolution, and the extreme limits of physical laws. Through the study of pulsars and magnetars, we gain a deeper understanding of the universe's most exotic remnants and the forces that shape them. These cosmic lighthouses remind us that the universe is filled with objects that challenge our understanding of matter, energy, and magnetism, illuminating the dark corners of the cosmos with their powerful emissions. The observable universe and the cosmic horizon. The observable universe is the portion of the cosmos from which light has had time to reach us since the Big Bang, creating a cosmic horizon that limits what we can see. Due to the finite speed of light and the age of the universe, about 13.8 billion years, this region spans approximately 93 billion light-years in diameter. Beyond this observable boundary lies the unobservable universe, potentially extending infinitely, where regions exist that will forever remain beyond our reach due to the accelerated expansion of space. This cosmic horizon is a fundamental limit, defined by the distance light can travel within the age of the universe. As the universe continues to expand, galaxies beyond a certain distance move away faster than light can travel, rendering them unreachable and eventually invisible. Over time, even galaxies within the observable universe will cross this horizon, slipping beyond our cosmic grasp. This process, driven by dark energy, means that future generations of observers will see a universe increasingly empty, with only our local group of galaxies remaining visible. The observable universe contains hundreds of billions of galaxies, each with billions or even trillions of stars, and yet it represents only a fraction of the entire cosmos. The vast scale of this region challenges our perception of distance and time, as the light we observe from distant galaxies left its source billions of years ago. When we look at the most distant objects, we are essentially looking back in time, witnessing events that occurred when the universe was far younger. The cosmic horizon also raises profound questions about the nature of the universe beyond our view. Some theories suggest that the unobservable regions of the universe may contain different physical laws or constants, hinting at the possibility of multiple pocket universes within a larger multiverse. Alternatively, if the universe is truly infinite, then there could be an infinite number of galaxies, stars, and potentially even civilizations beyond our sight. The concept of the observable universe is a reminder of the limits of human knowledge, as well as the vastness of the cosmos. It highlights the transient nature of cosmic observation, where the boundaries of what we can see are constantly shifting. As we continue to observe and understand the observable universe, we are also invited to ponder the infinite, unknowable regions that lie beyond, forever beyond our reach. The cosmic web, the universe's vast structure. The cosmic web is the large-scale structure of the universe, an interconnected network of galaxies, galaxy clusters, and dark matter, spanning billions of light years. This vast, intricate structure forms a web-like pattern, with dense regions where galaxies cluster together and vast cosmic voids in between, creating an appearance akin to a three-dimensional spider web. The cosmic web is the framework upon which the universe is built, shaped by gravity and the distribution of dark matter. The formation of the cosmic web is closely linked to the distribution of dark matter, which makes up about 85% of the universe's total matter content. Dark matter's gravitational influence acts as the scaffolding for ordinary matter, dictating where galaxies and clusters will form. Computer simulations, like the Millennium Simulation, have shown how dark matter clumps together over time, creating the filamentary structure observed in the cosmic web. These simulations provide a virtual model of the universe, allowing scientists to study how dark matter and gravity shape the cosmos from its earliest stages. The cosmic web not only structures the universe, but also plays a critical role in galaxy formation and evolution. Galaxies form within the denser regions of the web, where gas is more likely to accumulate and cool, allowing stars to ignite. The positions and movements of galaxies are influenced by the gravitational pull of surrounding dark matter, guiding them along the filaments of the web toward clusters. This cosmic migration means that galaxies are not isolated but are part of a vast, interconnected system, with their destinies intertwined by the gravitational dance of the cosmic web. Observing the cosmic web requires studying galaxies across vast distances, often using techniques like redshift surveys, which measure the velocity at which galaxies are moving away from us. By analyzing these redshifts, astronomers can map the three-dimensional distribution of galaxies and infer the structure of the web. Additionally, gravitational lensing, where the gravity of massive objects bends light from background sources, provides another way to map the distribution of dark matter, revealing the unseen threads of the cosmic web. The cosmic web is a testament to the universe's complexity and interconnectedness. It shows that galaxies, clusters, and superclusters are not scattered randomly, but are part of a vast structure governed by gravity and dark matter. This intricate network reminds us that the universe is far more than the sum of its parts, revealing an underlying order and unity that stretches across billions of light years. Entropy and the heat death of the universe. Entropy, a fundamental concept in thermodynamics, describes the tendency of systems to evolve from states of order to states of disorder. In a closed system, entropy tends to increase over time, meaning that energy becomes less available to do work, eventually leading to a state of maximum entropy where no further change is possible. This principle underlies the concept of the heat death of the universe, a hypothetical end state where all energy is evenly distributed, and the cosmos reaches thermodynamic equilibrium. The idea of heat death stems from the second law of thermodynamics, which suggests that as time progresses, the universe will become more disordered. Stars will burn out, galaxies will drift apart, and black holes will eventually evaporate through Hawking radiation. As the universe cools and expands, processes that require energy, such as star formation and chemical reactions, will cease, leaving a cold, dark, and inert cosmos. This scenario represents the ultimate end of all activity and change a universe frozen in time. The concept of heat death challenges our understanding of time and the universe's ultimate fate. It suggests that the universe is not eternal in its current form, but rather heading toward an inevitable end state. This idea raises profound philosophical questions about the nature of existence, as well as the purpose of life and consciousness in a universe destined for entropy. Entropy also plays a role in the arrow of time, as it provides a direction for temporal progression. While the fundamental laws of physics are time-symmetric, meaning they can operate equally well forward or backward, the second law of thermodynamics gives time its observed direction from past to future. This increase in entropy defines our perception of time, as we experience it in a forward-moving flow that aligns with the gradual increase in disorder. The heat death of the universe remains a distant future, potentially trillions of years away. Yet it serves as a reminder of the transient nature of cosmic structures. Galaxies, stars, planets, and even life itself are temporary arrangements of matter and energy, existing within the flow of entropy. As scientists continue to study entropy and its effects, they are reminded that even the universe's grandest structures are subject to the relentless pull of time and disorder. Gamma-ray bursts, the universe's most powerful explosions. Gamma-ray bursts, GRBs, are intense, short-lived bursts of gamma-ray radiation, the highest energy form of light. These events are among the most powerful explosions in the universe, releasing more energy in a few seconds than the sun will emit over its entire 10 billion-year lifespan. Gamma-ray bursts can outshine entire galaxies and are thought to originate from the collapse of massive stars or the collision of neutron stars, resulting in the formation of black holes. Gamma-ray bursts are classified into two types: short-duration bursts lasting less than 2 seconds, and long-duration bursts lasting more than 2 seconds. Short GRBs are believed to result from the collision of neutron stars or neutron-star black hole pairs, while long GRBs are associated with the collapse of massive stars in distant galaxies, often accompanied by supernova explosions. In both cases, the immense energy of these events generates intense beams of gamma rays that travel across vast distances. When a gamma-ray burst occurs, it releases a jet of gamma rays along its axis, often directed toward Earth. If a GRB's jet aligns with our line of sight, the burst appears extraordinarily bright, even from billions of light years away. This alignment amplifies the radiation, allowing it to be detected by gamma-ray telescopes. Because they are so powerful and occur randomly across the sky, GRBs have become essential tools for studying the far reaches of the universe, as their light travels through cosmic dust and gas, providing clues about the composition of distant regions. The study of GRBs has led to breakthroughs in understanding high-energy astrophysics, the evolution of stars, and the formation of black holes. Observations of GRBs have revealed that these bursts can trigger star formation in nearby regions by compressing gas clouds, igniting new stars in the aftermath of the explosion. Additionally, GRBs have been used to probe the properties of dark matter and to study the intergalactic medium, as the light from GRBs illuminates gas clouds and reveals their structure and composition. Gamma-ray bursts also pose potential risks to life on Earth. If a GRB were to occur within a few thousand light-years of our planet, it could have severe consequences, including stripping away parts of the atmosphere and exposing the surface to harmful radiation. While such an event is unlikely, studying GRBs provides insight into cosmic hazards and the extreme forces at play in the universe. Gamma-ray bursts remind us of the violent and energetic processes that shape the cosmos. They highlight the raw power of star death and the forces that drive cosmic evolution, revealing a universe that is both beautiful and dangerous. Each burst is a glimpse into the universe's most energetic phenomena, offering clues about the life cycles of stars and the formation of black holes. The Pioneer Anomaly, a cosmic mystery. The Pioneer Anomaly refers to an unexpected deviation in the trajectories of NASA's Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s to explore the outer solar system. After passing beyond the orbits of the outer planets, both probes began to experience a small, consistent acceleration toward the Sun, puzzling scientists and sparking debate about the nature of this mysterious force. The anomaly was subtle, an acceleration of only about 8.74 x 1010 m/s2, yet it persisted over decades, leading some researchers to question whether it could indicate new physics or unknown forces. Some speculated that dark matter, modifications to Newtonian gravity, or even the influence of exotic particles might explain the effect. Others suggested that thermal radiation from the spacecraft could be responsible, as the heat emitted unevenly from the probes could create a small but consistent push. After extensive study, researchers eventually concluded that the anomaly was likely due to asymmetric thermal radiation, as heat from the probe's power sources created a subtle, consistent thrust in the direction opposite their motion. This explanation, however, does not diminish the significance of the Pioneer anomaly, as it highlighted the need for precision in understanding the forces acting on spacecraft as they journey through space. The Pioneer anomaly reminds us of the challenges and uncertainties of space exploration. Even small, unexplained forces can impact our understanding of the cosmos, revealing gaps in our knowledge and inspiring new investigations. This mystery, though largely resolved, serves as a reminder that the universe is filled with subtle phenomena that can challenge our understanding of physics, encouraging scientists to approach the cosmos with curiosity and rigor. The Pioneer anomaly is a testament to humanity's desire to explore and understand, as well as to the precision required in studying the cosmos. It represents the unexpected questions that arise when we push the boundaries of exploration, revealing the complex interactions between matter, energy, and space itself. Primordial black holes, relics from the early universe. Primordial black holes, PB8s, are hypothetical black holes thought to have formed shortly after the Big Bang, during the universe's earliest moments. Unlike black holes formed from collapsing stars, which require a significant amount of time and massive stars, primordial black holes could have formed from regions of extremely high density in the young universe, created by fluctuations in matter distribution. These regions, compressed by gravity, might have collapsed into black holes just a fraction of a second after the Big Bang. Primordial black holes could vary widely in size, from tiny micro-black holes, smaller than an atom, to larger ones with masses comparable to mountains or even small planets. Their formation would depend on specific conditions in the early universe, where density fluctuations would need to be strong enough to overcome cosmic expansion, but not so intense as to prevent the universe's subsequent structure formation. One of the fascinating possibilities surrounding primordial black holes is their potential role as dark matter candidates. Dark matter, which constitutes about 27% of the universe's mass and energy, does not emit or absorb light, making it invisible and detectable only through its gravitational effects. If primordial black holes exist in large enough numbers, they could account for at least a portion of dark matter, as their gravitational pull could explain the missing mass observed in galaxies and clusters. Detecting primordial black holes is challenging, as they do not emit light and are expected to be scattered sparsely throughout the cosmos. However, several methods have been proposed to search for them. One approach involves looking for the gravitational lensing effects caused by primordial black holes passing in front of stars, temporarily brightening them as the black hole's gravity bends the starlight. Another method is searching for signs of Hawking radiation, as very small primordial black holes are expected to emit this radiation, slowly losing mass and eventually evaporating in a final burst of energy. If primordial black holes were to be discovered, they would offer an unprecedented window into the conditions of the early universe. These ancient objects could provide insights into the physics of high-energy density environments and help us understand the formation of cosmic structures. Moreover, they would bridge the gap between particle physics and cosmology, revealing how microscopic fluctuations in the primordial universe can lead to massive objects that endure billions of years. Primordial black holes remind us that the universe may hold remnants from its earliest moments, preserved as relics of the Big Bang. They represent the intersection of theory and observation, where the most ancient and enigmatic phenomena still exert a gravitational influence on the cosmos today. By studying them, we would gain clues about the universe's origin, its evolution, and the fundamental nature of matter and gravity. The fine-tuned universe, a question of cosmic coincidence. The concept of a fine-tuned universe refers to the observation that the fundamental physical constants and laws appear to be set at values that allow for the existence of complex structures, stars, planets, and, ultimately, life. If these constants were even slightly different, the universe would be vastly different, possibly incapable of supporting any form of complexity or life. This apparent fine-tuning raises questions about why the universe's laws seem so precisely calibrated. There are many examples of fine-tuning in the universe. For instance, the strength of the gravitational force, if only slightly weaker, would prevent galaxies, stars, and planets from forming. Conversely, if it were stronger, stars would burn their fuel too quickly for life to evolve. Similarly, the ratio of protons to electrons is precisely balanced, ensuring that the universe is electrically neutral on a large scale, which is essential for stable atomic and molecular structures. Another example is the cosmological constant, a parameter that describes the energy density of empty space and is linked to dark energy. If this constant were larger, the accelerated expansion of the universe would prevent galaxies from forming. If it were smaller, the universe could have collapsed under its own gravity shortly after the Big Bang. The narrow range within which the cosmological constant appears to fall is so specific that some scientists liken it to balancing a pencil on its tip, requiring an extraordinary level of precision. The fine-tuning of the universe has led to various interpretations. One possibility is the anthropic principle, which suggests that we observe these conditions because we exist within them. In other words, the universe appears fine-tuned because only a universe with such properties could support observers like us. Another explanation is the multiverse theory, which posits that there may be countless universes with different physical constants and laws. In this view, our universe is one of the few where the constants happen to allow for life, making it an observational coincidence. The idea of a fine-tuned universe raises questions about the nature of reality and whether there is an underlying purpose or cause for these precise values. Some propose that this fine-tuning could suggest the existence of a creator or an intelligent designer, while others argue that it could simply be a byproduct of natural processes or quantum fluctuations. The fine-tuning debate intersects with philosophy, cosmology, and theology, each offering different perspectives on why the universe appears as it does. Fine-tuning reminds us of the delicacy and interconnectedness of the universe's forces and constants. It suggests that the cosmos is not random but operates within a narrow range of possibilities that allow for complexity and consciousness. Whether by coincidence, necessity, or design, the fine-tuning of the universe continues to be one of the most profound mysteries, challenging us to ponder the origins and nature of reality itself. Fast radio bursts, the mysterious signals from deep space. Fast radio bursts, FRBs, are intense, brief pulses of radio waves originating from distant galaxies. Lasting only milliseconds, these bursts release an enormous amount of energy, equivalent to the sun's output in an entire day. Discovered in 2007, FRBs have become one of the most intriguing phenomena in astronomy, sparking a wide range of theories about their origins, from neutron stars to alien civilizations. Most FRBs are one-time events, known as non-repeating FRBs, which makes pinpointing their sources challenging. However, a small number of FRBs have been observed to repeat from the same location, allowing scientists to study them in greater detail. These repeating FRBs come from locations in galaxies that suggest association with magnetars, a type of neutron star with an exceptionally strong magnetic field. The exact mechanism behind FRBs remains unknown, but the involvement of magnetars is one of the leading hypotheses. FRBs are detected by radio telescopes, which scan the sky for transient signals. One of the most significant discoveries in recent years is FREB 121-102, a repeating FREB located in a distant dwarf galaxy. Its periodic bursts of energy have allowed astronomers to study its source, suggesting that the environment surrounding FREB 121-102 is highly magnetized, likely due to a nearby magnetar or an active galactic nucleus. This intense environment might be responsible for the energetic processes that produce these bursts. Another fascinating aspect of FRBs is their dispersion measure, which is the degree to which radio waves are scattered by intergalactic plasma. This scattering provides a rough estimate of the distance between the source and Earth, making FRBs valuable tools for mapping the distribution of matter in the universe. By studying the dispersion of FRBs from different regions, scientists can learn about the density of intergalactic plasma and the distribution of matter on cosmic scales. Some researchers have speculated that FRBs could be artificial in origin, potentially signals from advanced extraterrestrial civilizations. While there is currently no evidence to support this idea, the sheer energy and precision of FRBs have fueled imaginations. However, most astronomers believe that natural astrophysical processes are responsible, as the mechanisms involving neutron stars and magnetars can account for the observed properties of FRBs. The study of FRBs is still in its infancy, yet each new discovery brings us closer to understanding these enigmatic bursts. They reveal the energetic and dynamic nature of the universe, showing that even brief, fleeting events can carry vast amounts of information about cosmic environments. FRBs challenge our understanding of astrophysics, hinting at processes and objects that operate at the limits of known science. Dark flow, a mysterious motion beyond the cosmic horizon. Dark flow is an unusual phenomenon observed in the motion of galaxy clusters. suggesting that they are moving in a consistent direction at velocities that cannot be fully explained by the expansion of the universe alone. Discovered in 2008 through studies of the cosmic microwave background, CMB, dark flow appears to involve clusters moving toward a specific region of the sky, hinting at an influence from beyond the observable universe. The concept of dark flow challenges the standard cosmological model, which assumes that matter and energy are evenly distributed on the largest scales, resulting in no large-scale directional flow. However, measurements of galaxy cluster motions using the Sunyaev-Zeldovich effect, an interaction between the CMB and hot gas in galaxy clusters, indicate a motion that aligns across hundreds of millions of light years, directed toward the constellations Centaurus and Hydra. One possible explanation for dark flow is the gravitational influence of a massive structure beyond the cosmic horizon, potentially a supervoid or a supercluster larger than anything observed within the observable universe. Such a structure, if it exists, would lie beyond the reach of current telescopes, making it detectable only through its gravitational effects on observable matter. The existence of dark flow has sparked debates among cosmologists, as it could imply that the universe is not homogeneous on the largest scales. Instead, dark flow suggests that the universe may be part of a larger, interconnected structure, with regions beyond our cosmic horizon exerting influence on matter within our observable universe. Some researchers propose that dark flow could even be evidence for the multiverse, where neighboring universes or regions with different physical properties could exert a gravitational pull on our own universe. If these hypothetical neighboring universes exist, they might create gravitational effects that influence the motion of galaxy clusters within our observable realm, subtly tugging them in a particular direction. The idea of dark flow is controversial and still under investigation. Some studies have questioned the initial findings, suggesting that dark flow may not be as pronounced as originally thought, or that it could be explained by statistical anomalies. However, if dark flow is real, it represents a significant puzzle, as it challenges the cosmological principle, the idea that the universe is uniform on the largest scales. Dark flow implies that our universe might be influenced by structures or forces beyond the observable cosmos, raising profound questions about the nature of reality and the potential existence of realms we cannot see. Further research into dark flow will require more detailed observations of the cosmic microwave background and galaxy clusters across vast distances. Upcoming space missions, such as the Euclid and Nancy Grace Roman space telescopes, may provide insights into the distribution of matter and the potential existence of dark flow. By studying these large-scale movements, scientists hope to understand whether the dark flow is a real phenomenon or simply a statistical artifact. Dark flow reminds us that the universe may hold hidden structures and forces that lie beyond our current understanding. It challenges the boundaries of observational cosmology, suggesting that the universe we observe may be influenced by phenomena far outside our reach. Whether dark flow is an anomaly or a hint of a larger cosmic framework, it serves as a reminder that the universe is filled with mysteries that may stretch beyond the limits of our observable horizon. Vacuum energy and the mystery of dark energy. Vacuum energy is the energy present in empty space, even in the absence of matter or radiation. According to quantum mechanics, the vacuum is not truly empty, but is filled with fluctuating virtual particles that briefly pop into and out of existence. These fluctuations give rise to a tiny amount of energy known as vacuum energy, which contributes to the overall dynamics of the universe. This concept of vacuum energy is closely linked to dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up roughly 68% of the universe's total energy content, yet its nature remains one of the most profound mysteries in cosmology. Discovered in the late 1990s through observations of distant supernovae, dark energy appears to be causing galaxies to move apart at an increasing rate. This discovery revolutionized our understanding of the cosmos, suggesting that the universe's fate may be determined by a force that counteracts gravity on the largest scales. One leading hypothesis is that dark energy is a manifestation of vacuum energy. In this view, the energy of the vacuum exerts a negative pressure that accelerates the expansion of space. However, calculations of vacuum energy based on quantum field theory predict an energy density that is vastly higher than what is observed. leading to a discrepancy known as the cosmological constant problem. This mismatch between theoretical predictions and observations remains one of the biggest challenges in theoretical physics. Alternative explanations for dark energy include quintessence, a hypothetical scalar field that varies over time and space. Unlike vacuum energy, which is constant, quintessence would change as the universe evolves, potentially leading to different rates of expansion at different epochs. This concept aligns with some theories of modified gravity, which suggest that the laws of gravity may differ on cosmic scales, creating effects that resemble the influence of dark energy. Understanding dark energy and vacuum energy could have profound implications for the future of the universe. If dark energy remains constant, the universe will continue to expand indefinitely, leading to the Big Freeze scenario, where galaxies drift apart, stars burn out, and the universe becomes cold and dark. If dark energy changes over time, it could lead to alternative scenarios, such as the Big Rip, where dark energy eventually tears apart galaxies, stars, and even atoms themselves. Vacuum energy and dark energy remind us that even empty space is filled with mysteries. They challenge our understanding of the nature of space, time, and gravity, suggesting that the universe operates under principles that are still beyond our grasp. As scientists continue to probe the cosmos, the study of dark energy and vacuum energy may reveal new aspects of reality, reshaping our understanding of the universe and its ultimate fate. Time dilation and the twin paradox. Time dilation is a phenomenon predicted by Einstein's theory of relativity, where time passes at different rates depending on an object's speed or gravitational field. According to special relativity, as an object approaches the speed of light, time slows down for it relative to a stationary observer. This effect is known as time dilation due to relative velocity, and it has been confirmed by experiments with particles traveling at near light speeds, as well as by atomic clocks on high-speed aircraft and satellites. One of the most famous thought experiments involving time dilation is the twin paradox, where one twin travels on a high-speed journey through space, while the other remains on Earth. Upon returning, the traveling twin would find that they have aged more slowly than their sibling due to the effects of time dilation. Although it may seem counterintuitive, this phenomenon has been confirmed by experimental evidence and forms a cornerstone of modern physics. Time dilation also occurs in the presence of strong gravitational fields, an effect predicted by general relativity. Near massive objects like black holes, gravity warps space-time to such an extent that time passes more slowly. This phenomenon, known as gravitational time dilation, has been observed through experiments involving GPS satellites, which must account for both gravitational and velocity-based time dilation to provide accurate positioning data on Earth. The closer a clock is to a massive object, the slower it ticks, leading to measurable differences in time. The implications of time dilation extend to space travel and our understanding of the universe's structure. If humans were to embark on interstellar journeys at near light speeds, they could experience significant time dilation, effectively traveling into the future relative to those who remain on Earth. This concept has inspired science fiction stories and theoretical discussions about the nature of time, highlighting the flexibility and relativity of temporal experience. Time dilation also influences our understanding of the universe's evolution. In the vicinity of black holes and other dense objects, time dilation affects the rate at which matter falls into these objects, creating observable differences in how they grow and interact with their surroundings. Gravitational time dilation near the event horizon of a black hole, for example, means that an object falling toward the black hole would appear to slow down in redshift, eventually freezing in time from the perspective of a distant observer. The study of time dilation reminds us that time is not an absolute uniform flow, but is instead shaped by motion and gravity. It challenges our perceptions of reality, suggesting that time is flexible, and that our experience of it depends on our position and velocity within space-time. Time dilation reveals the complexity of the cosmos, where even the flow of time is influenced by the universe's forces and structures. The anthropic principle and the question of purpose. The anthropic principle is a philosophical consideration that attempts to explain why the universe's physical constants and laws appear to be fine-tuned for life. In its simplest form, the anthropic principle suggests that the universe must have properties that allow for the existence of observers, as we are here to observe it. This principle comes in two primary forms: the weak anthropic principle, which states that we can observe only a life-permitting universe, and the strong anthropic principle, which implies that the universe's properties may be inherently life-friendly. The anthropic principle arises from the observation that small changes in fundamental constants, such as the strength of gravity or the electromagnetic force, would render the universe inhospitable to life. If gravity were slightly stronger, stars would burn out too quickly, while if it were weaker, galaxies might never form. Similarly, the balance between matter and antimatter, the properties of subatomic particles, and the expansion rate of the universe are all finely tuned in ways that seem conducive to life. Some interpret the anthropic principle as evidence of design or purpose, suggesting that the universe's life-friendly properties are not coincidental but intentional. This interpretation often overlaps with theological or philosophical arguments, positing that the universe may have been created with life in mind. Others argue that the anthropic principle is simply a result of observational bias. We observe a life-permitting universe, because only such a universe could contain observers like ourselves. The anthropic principle also intersects with the multiverse theory, which posits that our universe may be one of many, each with different physical laws and constants. In a multiverse, it is conceivable that only a small fraction of universes have properties compatible with life. We happen to exist in one of those few universes, leading to the appearance of fine-tuning. This perspective suggests that our universe's properties are not unique, but are instead part of a vast ensemble, where countless other universes may exist with entirely different characteristics. The anthropic principle invites reflection on the nature of existence and the reasons behind the universe's properties. It challenges us to consider whether life and consciousness are fundamental outcomes of cosmic evolution or merely incidental byproducts. The anthropic principle is a reminder that the universe's structure and laws are delicately balanced, inviting questions about purpose, randomness, and the potential for deeper underlying principles. The holographic principle. Is the universe a projection? The holographic principle is a theory that suggests all the information contained within a volume of space can be represented on its boundary, much like a hologram. In this view, our three-dimensional universe could be a projection from a two-dimensional surface, where the information defining everything we experience is encoded. This radical idea challenges our understanding of space, matter, and reality, suggesting that the universe might not be what it appears to be. The holographic principle emerged from attempts to understand black holes and the paradoxes associated with them, specifically the black hole information paradox. According to classical physics, anything that falls into a black hole is lost beyond the event horizon, seemingly erasing information. However, quantum mechanics dictates that information should be conserved. To resolve this paradox, physicists proposed that information about the contents of a black hole might be stored on its event horizon, leading to the idea that a two-dimensional surface could encode the properties of three-dimensional objects. The holographic principle was later extended to the entire universe, suggesting that our reality could be a projection from a two-dimensional boundary in a higher dimensional space. This concept has been explored through string theory, where certain mathematical models support the idea that a lower dimensional boundary can contain all the information needed to describe a higher dimensional space. In these models, the universe behaves like a hologram, with everything we perceive as three-dimensional actually being encoded on a distant, two-dimensional surface. One fascinating implication of the holographic principle is that it could help reconcile quantum mechanics and general relativity. In a holographic universe, gravity emerges as a result of the interactions on the boundary, potentially offering a new way to understand gravity within the framework of quantum mechanics. This approach, known as the AT-CFT correspondence, anti-de Sitter conformal field theory, has provided insights into black holes, entanglement, and the nature of space-time itself. While the holographic principle remains theoretical, experimental research is underway to explore its implications. Some physicists are investigating whether the structure of space-time at the quantum level resembles a holographic encoding, with phenomena like entanglement revealing how information is shared across space. This research raises the possibility that our universe is fundamentally informational, with matter, energy, and space-time all emerging from a deeper, underlying code. The holographic principle invites us to question the nature of reality, challenging the assumption that the universe we perceive is the true reality. It suggests that what we experience is solid. Physical matter may ultimately be an illusion, a projection from a lower dimensional realm. This concept offers a radical perspective on existence, blurring the lines between the tangible and the abstract, and reminding us that the universe may be more complex and interconnected than we can currently comprehend. The Alcubierre warp drive, faster than light travel. The Alcubierre warp drive is a theoretical concept that proposes a way to achieve faster than light travel without violating the laws of physics, particularly Einstein's theory of relativity. Named after Mexican physicist Miguel Alcubierre, who introduced the idea in 1994, the warp drive relies on the concept of space-time manipulation rather than traditional propulsion. Instead of moving through space, the warp drive would create a bubble of warped space-time around a spacecraft, contracting space in front of it and expanding space behind it. In this warp bubble, the spacecraft itself would remain stationary relative to the space within the bubble, allowing it to move faster than light without technically exceeding the speed limit set by relativity. This approach sidesteps the problem of traveling through space at superluminal speeds, as the spacecraft would not be moving through space in the conventional sense, but would instead be carried along by the manipulated fabric of space-time itself. The idea of a warp drive is inspired by the mathematics of general relativity, which allows for the theoretical manipulation of space-time. However, creating a warp bubble would require an immense amount of energy, specifically a form of negative energy or exotic matter with properties that are not yet understood or available. Negative energy is a hypothetical form of energy that would have to repel rather than attract, allowing the space around the bubble to contract or expand in the desired manner. Although the warp drive remains speculative, recent advancements in quantum physics and experimental research have fueled interest in the concept. Some studies have proposed potential mechanisms for creating small amounts of negative energy, though the quantities required for a warp bubble are far beyond current capabilities. Nonetheless, the concept of manipulating space-time offers a glimpse into a future where interstellar travel might be possible, bypassing the limitations of conventional propulsion and relativistic speeds. The Alcubierre warp drive raises profound questions about the nature of space, time, and the limits of human exploration. If feasible, such a technology would enable humanity to reach distant star systems within a human lifetime, potentially opening up the galaxy for exploration and colonization. It invites us to consider a future where the boundaries of our solar system are no longer insurmountable and where new worlds lie within reach, redefining humanity's place in the cosmos. While the warp drive remains in the realm of theoretical physics, it serves as a reminder of the boundless potential of human imagination. Concepts like the Alcubierre warp drive encourage scientists to explore the limits of what is possible, pushing the boundaries of knowledge and inspiring future generations to pursue the dream of exploring the stars. Olber's paradox. Why is the night sky dark? Olber's paradox is a question that has intrigued astronomers and philosophers for centuries. If the universe is infinite, with an endless number of stars, why is the night sky dark? Named after German astronomer Heinrich Wilhelm Olbers, who popularized the question in the 19th century, the paradox challenges the notion of an eternal, static universe. In an infinite universe filled with stars, every line of sight should eventually meet the surface of a star, making the entire sky as bright as the sun. The resolution of Olber's paradox lies in our understanding of the expanding universe and the finite age of the cosmos. The universe is not only expanding but also has a finite age around 13.8 billion years, which means we can only observe stars within a certain distance, known as the observable universe. Stars beyond this distance are invisible to us because their light has not had enough time to reach Earth. Another key factor is the finite lifespan of stars. Stars are not eternal, they are born, evolve, and eventually die, either fading into white dwarfs or exploding in supernovae. As a result, the number of stars in the observable universe is limited, and not all regions of space are illuminated by stars. Furthermore, as the universe expands, the wavelengths of light from distant galaxies stretch due to redshift, shifting their light into the infrared or even radio wavelengths, which are invisible to the human eye. The discovery of the cosmic microwave background, CMB, also plays a role in resolving Olber's paradox. The CMB is the faint afterglow of the Big Bang, filling the universe with a background light that is now observed as microwaves. This radiation represents the surface of the observable universe at the time when it became transparent to light, around 380,000 years after the Big Bang. The CMB is faint and not visible to the naked eye, but it provides evidence that the universe was once filled with light and heat, gradually cooling over billions of years. Olber's paradox highlights the dynamic nature of the universe and the role of cosmic expansion in shaping our observations. It serves as a reminder that the night sky is not simply empty, but is influenced by the universe's history, structure, and evolution. The dark sky is a testament to the finite age of the cosmos, the expansion of space, and the limitations of human perception, showing us that the universe is more complex than it appears. The quantum vacuum and virtual particles. The quantum vacuum, also known as the vacuum state, is the lowest possible energy state in quantum mechanics, where no particles exist in the traditional sense. However, even this empty space is not truly empty. Instead, it is filled with fleeting particles that pop into and out of existence, known as virtual particles. These virtual particles represent fluctuations in the quantum fields that permeate space, resulting in brief, spontaneous events that contribute to the vacuum energy. Virtual particles are a consequence of Heisenberg's uncertainty principle, which states that certain properties of a system, such as energy and time, cannot be precisely determined simultaneously. This principle allows for short-lived violations of energy conservation, giving rise to virtual particles that exist for fractions of a second before annihilating. Although they cannot be observed directly, virtual particles have measurable effects, such as the Casimir effect of force observed between two closely spaced plates in a vacuum, caused by the pressure exerted by virtual particles. The study of the quantum vacuum has led to profound discoveries about the nature of space, energy, and the fundamental forces. In particular, virtual particles play a role in mediating the forces between particles, such as the electromagnetic force between charged particles. In quantum electrodynamics, QAD, virtual pawns act as messenger particles that facilitate interactions between electrons and other charged particles. Similar mechanisms apply to the strong and weak nuclear forces, where virtual particles mediate interactions between quarks and other subatomic particles. Virtual particles also contribute to the energy density of the vacuum, which is believed to be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. While the energy density predicted by quantum field theory is vastly higher than what is observed as dark energy, the link between vacuum fluctuations and cosmic expansion remains an area of intense research. The discrepancy between predicted and observed values, known as the cosmological constant problem, is one of the major unsolved mysteries in physics. The quantum vacuum challenges our understanding of emptiness, revealing that even the most empty regions of space are filled with fluctuations and interactions. Virtual particles highlight the dynamic nature of the quantum realm, where particles and forces arise from the fabric of space itself. The quantum vacuum serves as a reminder that the universe is a deeply interconnected system, where seemingly empty space holds the potential for creation, interaction, and the emergence of forces that shape the cosmos. Quantum entanglement, spooky action at a distance. Quantum entanglement is a phenomenon in which particles become interconnected in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. Described by Albert Einstein as spooky action at a distance, entanglement defies our classical understanding of locality and causality, suggesting that particles can remain linked across vast distances without any observable connection. Entanglement has profound implications for our understanding of reality and the fundamental nature of the quantum world. When two particles are entangled, measuring a property of one particle, such as its spin, will instantly determine the corresponding property of the other particle, even if they are separated by light years. This instantaneous connection seems to violate the speed limit set by the theory of relativity, as no information or influence should be able to travel faster than light. However, quantum entanglement does not involve the transmission of information in the conventional sense, which has led physicists to explore the deeper implications of this non-local effect. Quantum entanglement has been demonstrated in numerous experiments, including those with photons, electrons, and even larger molecules. One of the most famous experiments is known as the Bell test, which showed that measurements on entangled particles cannot be explained by any hidden variables that predetermine their outcomes. This result implies that entangled particles are fundamentally connected in a way that cannot be described by classical physics, pointing to the inherent weirdness of the quantum realm. Entanglement has also led to practical applications, such as quantum computing and quantum cryptography. In quantum computers, entangled particles, or qubits, can perform complex calculations much faster than classical bits, potentially revolutionizing fields such as cryptography, data analysis, and artificial intelligence. Quantum cryptography, on the other hand, uses entangled particles to create secure communication channels, as any attempt to intercept the entangled state would disrupt the system, alerting both parties to potential eavesdropping. In addition to technological applications, quantum entanglement raises philosophical questions about the nature of reality. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that entanglement reflects a deeper level of connection between parallel universes, where each possible outcome of a quantum event exists in a separate reality. Other interpretations, like the pilot wave theory, propose that particles are guided by an underlying wave that exists beyond our perception, creating an invisible link between entangled particles. Quantum entanglement challenges our intuition about space, time, and causality, revealing a universe where connections can exist beyond the limitations of physical distance. It suggests that reality is far more interconnected than it appears, with particles and forces influencing each other in ways that transcend our classical understanding. Entanglement invites us to explore the mysteries of the quantum realm, where the boundaries between particles, space, and even time blur, revealing a universe woven together by hidden, unseen links. The observable universe and the expansion of space. The observable universe is the portion of the cosmos from which light has had time to reach us since the Big Bang, creating a horizon beyond which we cannot see. Due to the finite speed of light and the universe's age, about 13.8 billion years, the observable universe spans roughly 93 billion light-years in diameter. Beyond this limit lies the unobservable universe, potentially extending infinitely or containing regions vastly different from our own. The observable universe is expanding, meaning that galaxies are moving away from us, with those farther from Earth receding at higher velocities. This expansion, first discovered by Edwin Hubble in the 1920s, is driven by dark energy, a mysterious force that appears to counteract gravity on cosmic scales. As space itself expands, the distances between galaxies increase, causing light from distant objects to stretch into longer wavelengths, a phenomenon known as redshift. This redshift provides crucial information about the universe's structure, age, and rate of expansion. One of the most intriguing aspects of the observable universe is that its boundary is constantly shifting. As time progresses, light from previously unseen regions will eventually reach Earth, revealing new cosmic landscapes. However, due to the accelerating expansion of space, some galaxies will eventually recede beyond the observable limit, becoming permanently inaccessible to future observers. This phenomenon creates a dynamic horizon, where the contents of the observable universe change over time as galaxies drift in and out of view. The expansion of the observable universe also raises questions about the nature of space and time. According to general relativity, the universe does not expand into anything. Rather, space itself is stretching, carrying galaxies with it. This expansion means that even the empty voids between galaxies are expanding, creating a universe where space is dynamic and evolving. This concept challenges our classical understanding of space as a static, unchanging backdrop, suggesting that space-time itself is an active participant in cosmic evolution. The observable universe is a reminder of the limits of human knowledge and the scale of the cosmos. It highlights the vastness of the universe, where billions of galaxies, each containing billions of stars, populate a region that is still only a fraction of the total universe. The expansion of space reveals the transient nature of observation, as galaxies and clusters shift in and out of reach, inviting us to ponder the infinite possibilities that lie beyond our cosmic horizon. The Casimir effect and the power of the quantum vacuum. The Casimir effect is a phenomenon that occurs when two uncharged, parallel metal plates are placed extremely close to each other in a vacuum. In this configuration, an attractive force arises between the plates, caused by the quantum fluctuations of the vacuum itself. Predicted by Dutch physicist Hendrik Casimir in 1948, the Casimir effect demonstrates that empty space is not truly empty but filled with virtual particles that create measurable forces. The Casimir effect arises from the quantum vacuum, where virtual particles constantly appear and annihilate, creating fluctuations in energy. When the plates are placed close together, the space between them restricts the wavelengths of these virtual particles, creating a lower energy density between the plates than in the surrounding vacuum. This difference in energy density generates a pressure that pushes the plates together, resulting in a measurable force that has been observed in laboratory experiments. The Casimir effect has profound implications for our understanding of the vacuum state and the nature of spacetime. It reveals that even in the absence of matter and radiation, the vacuum is filled with energy and fluctuations. This vacuum energy contributes to phenomena such as the Lamb shift in atomic energy levels and plays a role in fundamental forces. The Casimir effect demonstrates that the quantum vacuum is not a void but an active, dynamic field that influences particles and objects within it. The Casimir effect is also of interest for potential applications in nanotechnology and quantum mechanics. At very small scales, such as those encountered in microelectromechanical systems, MMS, the Casimir force becomes significant and can affect the behavior of tiny components. Understanding and controlling the Casimir effect could lead to advances in the design of microscopic devices, as well as new ways to harness quantum effects for practical applications. Additionally, the Casimir effect raises questions about the potential for vacuum energy as a source of power. While currently beyond our technological reach, some theorists speculate that it might be possible to tap into vacuum energy as a form of limitless energy. Such a breakthrough would revolutionize our understanding of energy and could lead to profound advancements in power generation, space travel, and technology. The Casimir effect serves as a reminder that even the emptiest regions of space are filled with invisible forces and energies. It challenges our classical understanding of nothingness, revealing a quantum realm where the vacuum is alive with fluctuations, interactions, and the potential for new forms of energy. The Casimir effect invites us to explore the hidden depths of space, where quantum effects shape the fabric of reality and offer glimpses into the universe's most fundamental properties. White dwarfs and the ultimate fate of stars. White dwarfs are the final evolutionary stage of low and medium mass stars, such as our Sun. After exhausting their nuclear fuel, these stars shed their outer layers in a process known as a planetary nebula, leaving behind a hot, dense core that slowly cools over billions of years. This core, known as a white dwarf, is an incredibly compact remnant with a mass comparable to that of the Sun but a volume similar to Earth. White dwarfs are composed primarily of electron-degenerate matter, where electrons are packed together so tightly that they exert a quantum pressure, known as electron degeneracy pressure, which prevents the star from collapsing further. This pressure, a consequence of the Pauli exclusion principle, allows white dwarfs to remain stable despite their lack of nuclear fusion. Over time, they gradually radiate away their residual heat, eventually cooling to become black dwarfs, hypothetical, fully cooled remnants that do not emit any light. The formation of a white dwarf marks the end of a star's life cycle, but white dwarfs can still play active roles in the cosmos. In binary systems, where a white dwarf orbits a companion star, the white dwarf can pull matter from its companion, forming an accretion disk. If enough material accumulates, the white dwarf can reach a critical mass known as the Chandrasekhar limit, around 1.4 times the mass of the Sun. At this point, it may undergo a thermonuclear explosion, resulting in a type Ioa supernova, a powerful explosion that releases a vast amount of energy and disperses elements into space. Type Ioa supernova are valuable tools in cosmology because they have consistent peak luminosities, allowing astronomers to use them as standard candles to measure cosmic distances. Observations of distant type Ioa supernovae provided the first evidence for the accelerating expansion of the universe, leading to the discovery of dark energy. White dwarfs, therefore, play a crucial role in understanding the large-scale structure and evolution of the cosmos. White dwarfs also offer insights into the ultimate fate of stars and the chemical evolution of galaxies. As stars evolve and die, they release elements such as carbon, oxygen, and nitrogen into space, enriching the interstellar medium and contributing to the formation of new stars and planets. This cycle of stellar death and rebirth is fundamental to the evolution of galaxies and the development of complex structures, including the building blocks of life. White dwarfs are silent witnesses to the life cycles of stars and the processes that shape galaxies. They remind us that even the quietest objects in the universe can have far-reaching effects, contributing to the enrichment of the cosmos and the expansion of our understanding. By studying white dwarfs, we gain a glimpse into the future of our sun and the legacy of stars as they transition from vibrant spheres of fusion to quiet, enduring remnants. Neutron stars, cosmic heavyweights. Neutron stars are the incredibly dense remnants of massive stars that have exploded in supernovae. When a star between about 8 and 20 times the mass of the Sun exhausts its nuclear fuel, it undergoes a gravitational collapse, forcing protons and electrons to combine and form neutrons. This process results in a neutron star, a compact object with a mass greater than the Sun, but only about 10 kilometers in diameter, meaning that a teaspoon of neutron star material would weigh billions of tons. The extreme density of neutron stars creates gravitational and magnetic fields that are among the most powerful in the universe. Their gravitational pull is so intense that light bends around them, allowing astronomers to observe the backside of a neutron star from certain angles. Neutron stars rotate at incredibly high speeds, with some spinning hundreds of times per second. These rapidly rotating neutron stars, known as pulsars, emit beams of radiation that sweep across space like cosmic lighthouses. The magnetic fields of neutron stars can reach up to 1 trillion times stronger than Earth's, creating conditions where ordinary atomic structures cannot exist. Electrons are forced to spiral around magnetic field lines, and the surface of the star is thought to be covered in a crust of iron atoms tightly compressed into a lattice structure. Beneath the crust lies a sea of neutrons, which may become a neutron superfluid due to the extreme pressure, allowing them to flow without friction. In addition to their magnetic fields, neutron stars can exhibit dramatic phenomena such as starquakes. These quakes occur when the crust of the neutron star undergoes shifts, releasing sudden bursts of energy. In magnetars, a type of neutron star with an exceptionally strong magnetic field, these starquakes can result in intense gamma-ray flares, among the most energetic events in the Milky Way. Neutron stars are critical to our understanding of extreme states of matter. They exist at the edge of what we know about nuclear physics, with pressures and densities that cannot be replicated in any laboratory on Earth. Studying neutron stars allows physicists to explore how matter behaves under the most extreme conditions, providing insights into the fundamental properties of particles and forces. Neutron stars remind us of the relentless power of gravity and the strange, exotic forms matter can take under extreme conditions. They stand as cosmic heavyweights, bearing the legacy of massive stars that once lit up the galaxy. Through the study of neutron stars, we gain a window into the mysterious realms of ultra-dense matter, revealing the hidden extremes of our universe. Cosmic inflation, the universe's rapid birth. Cosmic inflation is a theory that describes a period of extremely rapid expansion in the early universe, occurring just fractions of a second after the Big Bang. According to this theory, the universe expanded exponentially, doubling in size many times over in less than 1/1,000,000th of a second. This sudden burst of expansion smoothed out any irregularities and distributed matter evenly, creating the homogeneous, isotropic universe we observe today. The concept of inflation was proposed by physicist Alan Guth in the 1980s to address several puzzles in cosmology, such as the horizon problem and the flatness problem. The horizon problem arises because regions of the universe that are far apart appear to have the same temperature and density, despite not having had enough time to interact with each other according to the speed of light. Inflation solves this by suggesting that these regions were once close together before inflation expanded them beyond each other's reach. Inflation also addresses the flatness problem, which concerns the universe's geometry. Observations suggest that the universe is remarkably flat, meaning that space is not curved on large scales. For this to be the case, the initial conditions of the universe had to be incredibly precise. Inflation explains this by stretching any initial curvature, making the universe appear flat on the scales we observe. The inflationary period is thought to have left imprints in the cosmic microwave background, CMB, the faint glow left over from the Big Bang. tiny fluctuations in temperature within the CMB correspond to fluctuations that were stretched to cosmic scales during inflation. These fluctuations later became the seeds of galaxies, clusters, and superclusters as gravity amplified them, leading to the cosmic structures we see today. One of the goals of cosmology is to detect primordial gravitational waves, ripples in space-time produced by inflation. These gravitational waves would have left subtle patterns in the CMB, providing evidence of inflation's occurrence. While these signals are incredibly faint, upcoming experiments in observatories may soon be able to detect them, offering a direct glimpse into the universe's earliest moments. Cosmic inflation reshapes our understanding of the Big Bang and the universe's beginning, suggesting that the cosmos emerged not from a single explosion, but from an era of rapid, exponential expansion. It challenges our perception of time, space, and scale, showing that even the smallest fluctuations can shape the largest structures in existence. Through inflation, we glimpse the birth of the universe as a dynamic, ever-expanding realm filled with boundless potential. The faint young sun paradox, early Earth's climate mystery. The faint young sun paradox refers to a puzzling inconsistency between early Earth's climate and the sun's estimated brightness at that time. According to stellar evolution models, the sun was about 30% dimmer when Earth formed over 4 billion years ago. With a weaker sun, Earth should have been a frozen planet, incapable of supporting liquid water or life. However, geological evidence shows that early Earth had liquid oceans and a relatively warm climate, suggesting that something kept the planet from freezing. One proposed solution to this paradox involves greenhouse gases such as carbon dioxide and methane, which could have trapped more heat in Earth's atmosphere, compensating for the sun's lower output. Higher levels of volcanic activity and tectonic shifts in early Earth could have released these gases, creating a thicker, warmer atmosphere. Methane, in particular, is an extremely potent greenhouse gas and could have contributed significantly to early Earth's warmth if present in high concentrations. Another possibility is that the young sun was more active and emitted more ultraviolet radiation, which would have interacted with Earth's atmosphere, potentially producing greenhouse gases and warming the planet. This hypothesis aligns with evidence of higher solar activity in young stars, which tend to emit more radiation early in their life cycles before stabilizing. If early Earth's atmosphere could absorb this energy, it might explain the warmer climate despite a fainter sun. Some scientists have explored the idea of geological or biological processes contributing to the warming. Primitive life forms, such as early cyanobacteria, could have influenced atmospheric composition by producing methane as a byproduct. The development of microbial life in Earth's early oceans may have played a role in maintaining a stable climate, creating a self-sustaining biological thermostat that regulated atmospheric gases. The faint young sun paradox invites us to explore the delicate balance of factors that make Earth habitable. It reminds us that Earth's climate and atmosphere are products of complex interactions between geology, biology, and solar activity. This paradox highlights the resilience and adaptability of our planet's early environment, showing that life can emerge and thrive even under challenging conditions. Understanding the faint young sun paradox not only sheds light on Earth's history, but also has implications for the search for habitable planets. It suggests that planets orbiting fainter stars could potentially support life if they have the right atmospheric conditions. This insight broadens the scope of habitability beyond stars similar to our Sun, expanding the possibilities for finding life in the universe. The Great Attractor, a cosmic mystery. The Great Attractor is a gravitational anomaly located in the direction of the Centaurus and Hydra constellations, about 150 to 250 million light-years from Earth. It appears to be drawing our galaxy, the Milky Way, along with thousands of other galaxies, toward it at a speed of roughly 600 kilometers per second. This powerful pull suggests the presence of a massive concentration of matter, yet much of this region is obscured by the zone of avoidance, an area of the sky hidden by our galaxy's dense gas and dust. The Great Attractor's gravitational influence is so strong that it affects not only the Milky Way, but also the entire Laniakea supercluster, a collection of galaxies stretching over 500 million light-years. This supercluster is itself moving toward the Great Attractor, drawn by its mysterious gravitational pull. However, the exact nature of the Great Attractor remains uncertain, as it is shrouded in cosmic dust and remains challenging to study directly. One hypothesis is that the Great Attractor is a massive supercluster or concentration of dark matter, creating a gravitational well that attracts surrounding galaxies. Observations of galaxy movement suggest that dark matter may be concentrated in this region, though its exact distribution is difficult to map. The Great Attractor could also be part of an even larger structure, such as the Shapley supercluster, which lies beyond it and exerts additional gravitational influence on surrounding galaxies. The study of the Great Attractor has led astronomers to propose that it may be part of the cosmic web, a network of dark matter filaments connecting galaxies and clusters across vast distances. These filaments create rivers of galaxies, guiding their movement toward areas of high density. The Great Attractor could be a dense node within this web, where dark matter and ordinary matter converge, shaping the structure of the universe. The Great Attractor serves as a reminder of the mysteries that lie beyond our view, suggesting that the universe contains massive structures that continue to influence galaxies on scales beyond human comprehension. It challenges our understanding of cosmic organization, hinting at a universe where vast, unseen forces govern the movement of galaxies, clusters, and superclusters across billions of light years. The Great Attractor invites us to consider the hidden influences that shape the cosmos, expanding our understanding of the universe's large-scale structure. Through the study of this gravitational anomaly, we learn that the universe is a dynamic, interconnected system, filled with forces and structures that remain hidden from direct observation. The Great Attractor reminds us that even the most distant galaxies are part of a vast cosmic flow, guided by gravitational currents that span the universe. The shadow of a black hole, a groundbreaking observation. In April 2019, humanity captured the first image of a black hole, marking a monumental achievement in astrophysics. The black hole, located in the center of the galaxy M87, lies 55 million light-years from Earth and has a mass 6.5 billion of the Sun. The image, produced by the Event Horizon Telescope, EAT collaboration, shows a bright ring of light encircling a dark shadow, the event horizon beyond which nothing can escape the black hole's gravitational pull. The EAT is a network of radio telescopes across the globe, synchronized to act as a single, Earth-sized telescope. By observing the black hole in M87 with unprecedented resolution, scientists were able to capture light bending around the event horizon, creating the characteristic shadow of the black hole. This groundbreaking image provided visual confirmation of Einstein's predictions about black holes and offered a glimpse into one of the universe's most extreme environments. The shadow of a black hole forms because of its immense gravitational pull, which warps space-time so intensely that light is bent around it. The bright ring seen in the image is composed of superheated gas and plasma swirling around the black hole at nearly the speed of light. The gas emits light as it accelerates and heats up, creating a glowing ring. The center of the ring appears dark because any light that crosses the event horizon is absorbed, creating a silhouette. This first image of a black hole has profound implications for our understanding of gravity, space-time, and the fundamental laws of the universe. By studying the shape and structure of the black hole's shadow, scientists can test the predictions of general relativity in a region where gravity is exceptionally strong. Future observations may reveal subtle deviations from Einstein's equations, potentially pointing to new physics or insights into quantum gravity. The EAT continues to observe other black holes, including Sagittarius A, the supermassive black hole at the center of our Milky Way. Each new image and observation advances our understanding of these enigmatic objects, bringing us closer to unraveling the mysteries of black holes and the forces that govern them. The shadow of a black hole is a testament to human ingenuity and a reminder that even the darkest realms of the universe can be explored through the lens of science. This observation marks a new era in astronomy, where black holes can be studied not just through indirect effects, but directly, through images that capture their shadows against the glowing fabric of the cosmos. It shows that the boundaries of human knowledge are constantly expanding as we push deeper into the unknown and illuminate the darkest corners of existence. The dark matter halo, the hidden structure of galaxies. Dark matter halos are vast, invisible structures that surround galaxies, binding them together and influencing their shape, rotation, and interactions. While dark matter cannot be observed directly, its gravitational effects are essential to explaining the motion of stars and gas within galaxies. Without the influence of dark matter, galaxies would not have enough mass to hold their structures together, and they would simply fly apart. The concept of a dark matter halo arose from observations in the 1970s, when astronomer Vera Rubin studied the rotation curves of galaxies. Rubin found that stars far from the center of galaxies were orbiting at higher velocities than expected, suggesting that a large amount of unseen mass was exerting gravitational force. This unseen mass was attributed to dark matter, which does not interact with light, but contributes to the overall gravitational field of galaxies. Dark matter halos extend far beyond the visible portions of galaxies, enveloping them in a bubble of gravitational influence. These halos are thought to play a crucial role in galaxy formation and evolution. They help galaxies maintain stability, support the formation of stars by compressing gas clouds, and prevent smaller galaxies from being torn apart during mergers and interactions. In clusters of galaxies, dark matter halos also help bind the galaxies together, creating massive cosmic structures. Cosmological simulations, such as the Millennium Simulation, have shown how dark matter halos form and interact in the large-scale structure of the universe. These simulations reveal a web-like pattern of dark matter filaments that connect galaxies in clusters, creating the cosmic web. Dark matter halos act as nodes in this network, pulling in ordinary matter and shaping the distribution of galaxies across vast distances. The study of dark matter halos has led to the concept of galaxy bias, which suggests that galaxies are biased tracers of the underlying dark matter. While galaxies reveal only a small fraction of the universe's total mass, dark matter halos provide a more complete picture of cosmic structure. By mapping these halos through gravitational lensing and other techniques, astronomers gain insight into the invisible framework that holds the universe together. Dark matter halos remind us that much of the universe lies beyond our senses, governed by forces we cannot see but can infer through their effects. They represent the hidden architecture of the cosmos, a structure that binds galaxies, clusters, and superclusters in a web of gravitational connections. The study of dark matter halos is an exploration of the invisible forces that shape the universe, revealing the intricate scaffolding upon which all visible structures rest. The observable horizon in the universe's edge. The observable horizon is a dynamic boundary that changes over time as the universe expands. In the distant past, the observable universe was much smaller, with galaxies packed closer together. As time progresses, galaxies beyond a certain distance move away faster than light, effectively disappearing from view as they cross the horizon. This phenomenon is a consequence of cosmic expansion, which stretches space itself and creates a moving limit on what can be observed. One of the challenges in studying the observable horizon is understanding what lies beyond it, since we cannot receive light or other signals from beyond this boundary. Any knowledge of regions beyond the observable universe remains speculative. Some theories suggest that the universe could be infinite, extending far beyond our observational limits, while others propose that the universe may have a specific shape or structure that repeats or curves back on itself. The observable horizon also raises philosophical questions about the nature of reality. Since we are limited to observing only a finite portion of the universe, we may be seeing only a small fraction of a much larger, possibly infinite cosmos. This limitation challenges our understanding of the universe as a whole, reminding us that our perspective is inherently constrained by the speed of light and the age of the cosmos. The edge of the observable universe is not a physical boundary but a limit imposed by the laws of physics. It serves as a reminder of the vastness of the cosmos and the inherent limitations of human observation. The observable horizon invites us to ponder the mysteries that lie beyond our reach, hinting at realms of space and time that will forever remain hidden from view. The concept of the observable horizon is a humbling one, showing us that even the most advanced telescopes and technologies cannot reveal the entirety of the universe. It suggests that there may always be more to discover, encouraging us to explore the limits of knowledge while accepting the mysteries that remain beyond the cosmic horizon. Redshift and the expanding universe. Redshift is a phenomenon in which the wavelength of light from distant galaxies is stretched, shifting it toward the red end of the spectrum. This effect, first observed by Edwin Hubble in the 1920s, provides key evidence for the expansion of the universe. As galaxies move away from us, the space between them stretches, causing the light they emit to appear redshifted. The greater the redshift, the farther away and faster the galaxy is receding, allowing astronomers to measure cosmic distances and velocities. Redshift is crucial for understanding the universe's structure and history. By observing the redshift of galaxies, scientists can trace the rate of cosmic expansion over time, revealing the influence of dark energy and providing insights into the fate of the cosmos. The relationship between redshift and distance is known as Hubble's law, which states that the speed at which a galaxy recedes is proportional to its distance from us. The discovery of redshift led to the concept of the expanding universe, challenging the idea of a static cosmos. This expansion is not an explosion outward, but rather an increase in the distance between all points in space. As the universe expands, galaxies drift apart, carried along by the stretching of space itself. This expansion means that the farther a galaxy is from Earth, the faster it is receding, with some galaxies now beyond the reach of light due to the speed of expansion. There are different types of redshift, each with its own cause. The most familiar is cosmological redshift, caused by the expansion of space. Another type is gravitational redshift, which occurs when light escapes from a strong gravitational field, losing energy and shifting toward red as it moves. This effect has been observed near massive objects like black holes, where intense gravity alters the wavelength of light. Redshift has also revealed key insights into the early universe. Observing distant galaxies and quasars at high redshifts allows astronomers to look back in time, seeing these objects as they were billions of years ago. These observations provide a glimpse into the young universe, showing how galaxies and structures formed and evolved over cosmic history. Redshift effectively turns telescopes into time machines, allowing scientists to study the universe's past. The study of redshift is foundational to cosmology, offering a window into the universe's dynamics and the forces that shape it. It shows us that the cosmos is not a static backdrop, but a constantly evolving entity, expanding and changing over billions of years. Redshift reveals the story of the universe's growth, from its earliest moments to its present state, and hints at its future, where galaxies may drift beyond reach in an ever-expanding sea of space. Wormholes, shortcuts through space-time. Wormholes are theoretical tunnels in space-time that could, in principle, connect two distant points, allowing for faster-than-light travel. First proposed by physicist Ludwig Flamm in 1916 and later explored by Albert Einstein and Nathan Rosen, wormholes are solutions to Einstein's equations of general relativity. They are sometimes called Einstein-Rosen bridges and are visualized as pathways through space-time, like shortcuts that bypass the intervening distance. In theory, a wormhole would consist of two mouths connected by a throat, creating a bridge between distant regions of space. If one could enter a wormhole, they might emerge almost instantaneously at the other end, covering vast cosmic distances in an instant. This idea has inspired countless works of science fiction, as wormholes offer the tantalizing possibility of interstellar travel, allowing civilizations to explore the galaxy without the limitations of light-speed travel. However, wormholes present numerous scientific challenges. To remain stable and traversable, a wormhole would require a form of exotic matter with negative energy density. This exotic matter would prevent the wormhole from collapsing and allow it to remain open, but such matter has not been observed and may not even be possible. Without exotic matter, wormholes would likely be unstable, collapsing as soon as any matter attempted to pass through. Wormholes are not just theoretical constructs, they have practical applications in the study of space-time and gravity. The mathematics of wormholes helps physicists explore the limits of general relativity and investigate how gravity behaves in extreme environments. Some researchers suggest that wormholes could play a role in black hole physics, with certain types of black holes potentially acting as gateways to other regions of space or even other universes. Another intriguing aspect of wormholes is their potential use for time travel. By manipulating one end of a wormhole, it may be possible to create a time difference between the two ends, allowing one to travel backward or forward in time. This concept, while speculative, has led to debates about causality, paradoxes, and the fundamental nature of time. If time travel were possible through wormholes, it would challenge our understanding of cause and effect, raising questions about the possibility of altering history. Wormholes remain a tantalizing but elusive idea in theoretical physics. They represent the dream of exploring the universe beyond the speed of light, connecting distant worlds and expanding our reach across space and time. While they are currently beyond our technological capabilities, wormholes remind us that the universe may hold secrets yet to be discovered, pathways that could one day unlock new realms of exploration. The cosmic microwave background, the afterglow of creation. The cosmic microwave background, CMB, is the faint radiation left over from the Big Bang, filling the universe as a background glow. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB provides a snapshot of the universe when it was just 380,000 years old, a time when it cooled enough for atoms to form and light to travel freely. This afterglow of creation is one of the most important pieces of evidence for the Big Bang theory and serves as a baby picture of the universe. The CMB is remarkably uniform, with tiny fluctuations in temperature that reflect density variations in the early universe. These fluctuations served as the seeds for galaxies and clusters, as gravity amplified the denser regions over billions of years, leading to the cosmic structures we observe today. By studying the patterns in the CMB, scientists can learn about the conditions of the early universe, the nature of dark matter and dark energy, and the processes that led to the formation of galaxies. One of the most important discoveries made through the CMB is the flatness of the universe, indicating that space is not curved on large scales. This flatness supports the theory of cosmic inflation, which suggests that the universe underwent a rapid expansion shortly after the Big Bang. Inflation would have smoothed out any initial curvature, creating the flat, uniform cosmos we observe. The CMB also reveals information about the age, composition, and rate of expansion of the universe, providing a framework for modern cosmology. The CMB is studied using specialized telescopes and satellites, such as the Planck satellite, which mapped the CMB in extraordinary detail. These observations have allowed scientists to measure parameters like the Hubble constant and the density of dark matter and dark energy, refining our understanding of the universe's history and structure. The CMB also holds clues to phenomena such as primordial gravitational waves, which could provide evidence for the inflationary period. The cosmic microwave background is a reminder of the universe's origins, a relic of a time when the cosmos was young, hot, and dense. It connects us to the beginning of everything we know, offering a glimpse into the birth of space, time, and matter. Through the study of the CMB, we are able to reach back to the dawn of the universe, uncovering the fundamental processes that shaped the cosmos and led to the world we inhabit today. Gravitational waves, ripples in the fabric of space-time. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as merging black holes or neutron stars. Predicted by Albert Einstein in 1916 as part of his theory of general relativity, gravitational waves remained undetected for nearly a century. In 2015, the LIGO Laser Interferometer Gravitational Wave Observatory collaboration made the first direct observation of gravitational waves, confirming a key aspect of Einstein's theory and opening a new era in astronomy. When massive objects accelerate, especially in events as cataclysmic as the collision of black holes, they create disturbances that propagate through space-time, similar to ripples on a pond. These waves travel at the speed of light and carry information about the objects that created them, offering a new way to observe cosmic phenomena. Gravitational waves are incredibly faint by the time they reach Earth, requiring advanced technology to detect the tiny distortions they cause in space-time. Gravitational wave astronomy has since become a groundbreaking field, allowing scientists to observe events that were previously invisible, such as black hole mergers and neutron star collisions. These observations provide insights into the nature of black holes, the formation of heavy elements, and the behavior of matter under extreme gravitational forces. The detection of gravitational waves from neutron star collisions has also confirmed that such events are responsible for producing heavy elements like gold and platinum, enriching the cosmos. One of the most exciting aspects of gravitational wave astronomy is the potential to study the early universe. It is believed that primordial gravitational waves, produced during cosmic inflation, could carry information about the universe's first moments. Detecting these waves would provide a direct glimpse into the conditions of the early universe, offering evidence for inflation and revealing fundamental aspects of space-time. Gravitational waves remind us that the universe is dynamic, filled with violent and energetic processes that shape its structure. They allow us to listen to the cosmos, detecting events that cannot be seen with traditional telescopes. Gravitational wave astronomy expands our senses, giving us a new way to explore the universe and deepen our understanding of the fundamental forces that govern it. The supermassive black hole at the galactic center. At the heart of the Milky Way lies Sagittarius A, a supermassive black hole with a mass equivalent to 4 million suns. Located approximately 26,000 light-years from Earth, this massive object governs the motion of stars and gas clouds in the center of our galaxy. The discovery of Sagittarius A and its role as the galactic center's anchor has reshaped our understanding of galaxy dynamics and the role of black holes in galactic evolution. Observing the motions of stars around Sagittarius A has provided definitive evidence of its presence. By tracking these stars over several decades, astronomers have calculated the mass and location of the black hole with incredible precision. The orbits of these stars, which come perilously close to Sagittarius A, confirm that only a supermassive black hole could exert the gravitational pull necessary to keep them in such extreme, elliptical paths. Sagittarius also emits powerful radio waves, which have been observed by radio telescopes worldwide. This emission is caused by the acceleration of particles near the black hole's event horizon, where intense gravitational and magnetic fields create a swirling maelstrom of energy. While Sagittarius A is relatively quiet compared to other supermassive black holes in active galaxies, it occasionally flares, releasing bursts of radiation that provide valuable data on black hole activity. The presence of a supermassive black hole at the center of the Milky Way raises intriguing questions about its origin and evolution. Scientists believe that most large galaxies harbor supermassive black holes at their centers, suggesting a connection between black holes and galaxy formation. Some theories propose that supermassive black holes may have formed through the mergers of smaller black holes or from massive gas clouds that collapsed in the early universe. Sagittarius serves as a window into the behavior of black holes and their impact on galaxies. By studying this massive object, astronomers can learn about the interactions between black holes and their host galaxies, including how black holes influence star formation and galactic structure. Observations of Sagittarius continue to push the boundaries of astrophysics, revealing the hidden forces that shape galaxies and govern the dynamics of the cosmos. The supermassive black hole at the center of the Milky Way reminds us that our galaxy, and perhaps every galaxy, is anchored by a powerful gravitational force. Sagittarius A is a cosmic powerhouse, binding the Milky Way together and offering a glimpse into the enigmatic role of black holes in the universe. As scientists continue to observe and study this giant, they uncover more about the mysteries of galaxy formation, the nature of gravity, and the ultimate fate of our galaxy. Cosmic strings, the universe's theoretical threads. Cosmic strings are hypothetical, one-dimensional defects in space-time that could have formed in the early universe during phase transitions, similar to the way cracks form in ice as it freezes. Predicted by some grand unified theories, cosmic strings would be extremely thin but incredibly dense, with a single cosmic string potentially stretching across the universe while carrying the mass of a planet. These cosmic strings would create powerful gravitational fields, bending space-time and affecting the motion of nearby objects. If cosmic strings exist, they could provide a unique signature in the cosmos, as their immense gravitational pull would cause gravitational lensing, bending light from distant objects. This lensing effect could create unusual patterns in the light from background galaxies, allowing astronomers to detect the presence of cosmic strings indirectly. Additionally, as cosmic strings move, they would generate gravitational waves, producing signals that could be observed by gravitational wave detectors. Cosmic strings are thought to be remnants of the early universe, left over from phase transitions that occurred as the universe cooled. These phase transitions would have broken the initial symmetry of the universe, creating defects in space-time. Cosmic strings are a type of topological defect, like domain walls or monopoles, which are also predicted by certain cosmological theories. Their existence would provide evidence for the processes that shaped the universe in its infancy. The study of cosmic strings intersects with theories of dark matter and dark energy. Some researchers propose that cosmic strings could interact with dark matter, influencing its distribution and contributing to the formation of cosmic structures. Others suggest that cosmic strings could play a role in the cosmic web, acting as highways along which galaxies and clusters are organized, providing a framework for the universe's large-scale structure. Cosmic strings remain a speculative concept, but they represent the frontier of theoretical physics. If discovered, they would offer a direct link to the conditions of the early universe, providing insights into the forces that shaped cosmic evolution. The search for cosmic strings continues, driven by the hope that these mysterious threads may one day reveal a deeper understanding of the universe's origins and the forces that govern space-time. Multiverse theory, a universe of universes. The multiverse theory suggests that our universe may be just one of countless others, each with its own set of physical laws, constants, and even dimensions. This concept arises from several areas of theoretical physics, including quantum mechanics, string theory, and cosmology. If true, the multiverse would mean that what we consider to be the universe is just a small part of a vast ensemble of universes, each existing within a much larger meta-universe. One version of the multiverse theory comes from quantum mechanics, specifically the many worlds interpretation. According to this interpretation, every possible outcome of a quantum event actually occurs, creating a branching set of parallel universes. For example, if you flip a coin, there would be one universe where it lands heads and another where it lands tails. This branching would continue with every quantum decision, creating an ever-expanding tree of parallel realities. Another multiverse concept comes from cosmic inflation theory. Inflation suggests that shortly after the Big Bang, the universe underwent a rapid expansion. During this period, different regions could have stopped inflating at different times, creating bubble universes isolated from one another. Each bubble would then evolve independently, potentially with its own set of physical properties. This concept, known as eternal inflation, implies that there could be an infinite number of such bubbles, each representing a unique universe. String theory also supports the multiverse idea by proposing that there could be additional dimensions beyond the three of space and one of time that we experience. These extra dimensions could give rise to alternate universes with entirely different physical laws and constants. In this view, our universe may be a brane, or three-dimensional membrane, floating in a higher dimensional space. Other branes or universes could exist in this same space, possibly even interacting with our own under certain conditions. The multiverse theory raises profound questions about the nature of reality and our place within it. If the multiverse exists, it implies that our universe's physical constants are not unique, but are simply one possibility among many. This notion could help explain the fine-tuning of the universe, as only certain universes in the multiverse would have conditions suitable for life. We happen to live in one of those universes, giving us a biased perspective on the multiverse as a whole. While the multiverse remains speculative and difficult to test, it challenges our understanding of reality, suggesting that the universe we observe may be only a small part of a much larger, more complex structure. The concept of a multiverse invites us to contemplate the idea of infinite possibilities, where each decision and event leads to a cascade of alternate realities, expanding our view of existence beyond the boundaries of our known cosmos. The shape of the universe, flat, open, or closed. One of the most fundamental questions in cosmology is the shape of the universe. Is it flat, open, or closed? The answer depends on the amount of matter and energy in the universe, as well as the influence of dark energy, which drives the expansion of space. The shape of the universe has profound implications for its ultimate fate, determining whether it will expand forever, collapse back on itself, or reach a stable size. If the universe is flat, it means that space is not curved on large scales, and parallel lines will never intersect. This shape aligns with observations of the cosmic microwave background, CMB, and the distribution of galaxies, which suggest that the universe's geometry is flat. A flat universe would expand forever, but the rate of expansion would gradually slow down over time, potentially reaching a state of near equilibrium. An open universe has a negative curvature, resembling a saddle shape. In an open universe, parallel lines eventually diverge, and the universe would continue to expand forever, accelerating as it does so. This shape implies an infinite, unbounded universe with no ultimate boundary. However, observations so far indicate that the universe is not open, as the evidence points toward a flat or very nearly flat geometry. A closed universe has positive curvature, resembling the surface of a sphere. In a closed universe, parallel lines would eventually intersect, and if the density of matter and energy were high enough, the universe could eventually stop expanding and begin to collapse, leading to a big crunch. This scenario would mean that the universe is finite but unbounded, wrapping back on itself like the surface of a sphere. The current consensus, based on data from the CMB and observations of distant supernovae, is that the universe is flat, or very close to flat, with dark energy causing its expansion to accelerate. However, even a nearly flat universe could still be finite, depending on its overall geometry and topology. Some theories suggest that the universe may be flat but wrap back on itself in a higher dimensional space, forming a finite but unbounded structure. The shape of the universe is not just a geometric question, it is also a question of destiny. Whether the universe will expand forever or eventually collapse depends on its shape, the properties of dark energy, and the total density of matter. The study of the universe's shape challenges us to understand the nature of space-time itself, exploring the possibilities of a cosmos that is boundless, finite, or infinite in scope. The shape of the universe reminds us that the cosmos is not necessarily a simple, straightforward space but could have complex, hidden dimensions that defy our intuitive understanding. As we study the universe's structure, we uncover more about its origins, its future, and the ultimate nature of the space in which all matter and energy reside. The Kardashev Scale, measuring civilizational advancement. The Kardashev Scale is a theoretical framework for measuring the technological advancement of civilizations based on their energy consumption. Proposed by Soviet astronomer Nikolai Kardashev in 1964, the scale categorizes civilizations into three primary types, based on their ability to harness energy from their surroundings. The scale provides a way to imagine civilizations far more advanced than humanity and the potential future of our own civilization. A Type I civilization, or planetary civilization, is capable of utilizing all of the available energy on its home planet. This would include harnessing the power of natural resources, controlling the planet's climate, and potentially even managing geological processes like earthquakes and volcanic activity. Humanity is not yet a Type I civilization, but is estimated to be around 0.7 on the Kardashev scale, as we are just beginning to harness global energy sources. A Type I civilization, or stellar civilization, would be able to capture and use the energy output of an entire star. One proposed method for achieving this would be the construction of a Dyson sphere, a hypothetical structure that surrounds a star, capturing its energy and providing virtually limitless power. A Type I civilization could use this energy to sustain large-scale projects, interplanetary travel, and possibly even interstellar colonization. A Type I civilization, or galactic civilization, would have the ability to harness the energy output of an entire galaxy. This level of advancement would require a profound mastery of technology, allowing the civilization to control star systems, manipulate black holes, and access nearly limitless resources. A Type I civilization would likely have capabilities beyond human comprehension, including the potential to reshape the galaxy itself. The Kardashev scale has inspired speculation about the existence of advanced extraterrestrial civilizations. If Type I or Type I civilizations exist, they might be detectable through their energy signatures, such as waste heat from large-scale energy structures. Observing the light or infrared emissions from distant galaxies could reveal unusual patterns that hint at the presence of advanced technological activity. Some extensions of the Kardashev scale propose additional types, such as Type IV civilizations that harness the energy of an entire universe, or even Type V civilizations that manipulate multiple universes within a multiverse. These speculative types stretch the imagination, suggesting levels of advancement that go far beyond our current understanding of physics and technology. The Kardashev scale invites us to consider the future of humanity and the potential for civilizations beyond Earth. It challenges us to think about our place in the cosmos, imagining a progression of technological development that spans from planetary mastery to the control of entire galaxies. The scale serves as a reminder that the universe may contain forms of life and intelligence far more advanced than anything we can currently comprehend. The Omega Point, theoretical end of intelligence. The Omega Point is a hypothetical future state in which all intelligence and information in the universe converges, reaching a state of infinite knowledge and capability. Proposed by physicist and philosopher Frank Tipler, the Omega Point suggests that as the universe evolves, intelligent life could eventually reach a state where it can control the entire cosmos. This concept combines ideas from thermodynamics, cosmology, and information theory, envisioning a final, transcendent stage of evolution. The Omega Point relies on the assumption that the universe's resources could be harnessed to support ever-increasing computational power. As civilizations advance, they would use energy and matter more efficiently, approaching a state where they can perform an infinite number of computations in a finite amount of time. If such a state could be achieved, it would represent a convergence of all intelligence, knowledge, and consciousness, potentially merging all minds into a single, unified entity. Tipler's theory is highly speculative and has faced criticism for its assumptions about the nature of the universe and the potential for infinite computation. However, it raises interesting questions about the future of intelligence and the ultimate goals of advanced civilizations. The Omega Point is sometimes compared to the concept of a technological singularity, where rapid advancements in artificial intelligence lead to a future that is incomprehensible to human minds. The Omega Point also touches on philosophical and theological questions, as it resembles certain ideas of a transcendent, all-knowing state. Some interpretations of the Omega Point even propose that it could lead to a form of digital immortality, where all past beings could be simulated and resurrected within this final state. This idea blurs the boundaries between science, philosophy, and spirituality, suggesting that the evolution of intelligence may be a path toward a kind of cosmic enlightenment. While the Omega Point remains purely theoretical, it represents an exploration of the limits of intelligence and consciousness. It suggests that the universe could be not only a physical realm but also a medium for the evolution of thought, knowledge, and self-awareness. The Omega Point invites us to consider the ultimate destiny of intelligent life, pondering whether the universe's true purpose lies not just in the existence of matter and energy, but in the culmination of consciousness itself. The concept of the Omega Point encourages us to think about the long-term trajectory of intelligence, wondering if there could be a final state of universal awareness that transcends the limits of individual minds. It suggests that the universe may hold a destiny that goes beyond physical existence, where knowledge, creativity, and consciousness reach their highest potential. Hawking radiation and the fate of black holes. Hawking radiation, a phenomenon predicted by physicist Stephen Hawking in 1974, suggests that black holes can emit radiation and, over incredibly long time scales, eventually evaporate entirely. This groundbreaking theory challenged the previous assumption that nothing could escape from a black hole. According to Hawking, the intense gravitational field near a black hole's event horizon can cause virtual particle pairs to form from quantum fluctuations. If one of these particles falls into the black hole while the other escapes, it appears as though the black hole is emitting radiation. Hawking radiation occurs because of quantum effects near the event horizon. When a pair of particles emerges near the event horizon, the negative energy particle may be captured by the black hole, while the positive energy particle escapes into space. This process effectively reduces the mass of the black hole, causing it to evaporate over time. As the black hole loses mass, the radiation intensifies until the black hole eventually vanishes in a final burst of energy. This theory of black hole evaporation has significant implications for the nature of information and the laws of thermodynamics. One of the key questions in physics is whether information that falls into a black hole is permanently lost when the black hole evaporates, or if it can somehow be preserved. This question, known as the black hole information paradox, has led to extensive debates and research, as the loss of information would violate fundamental principles of quantum mechanics. Hawking radiation has yet to be observed directly, as it is extremely faint and difficult to detect from black holes of stellar or supermassive size. However, this phenomenon is a crucial element in understanding the life cycle of black holes and their eventual demise. If Hawking's theory is correct, it implies that all black holes will eventually evaporate over trillions of years, leaving behind no trace of their original mass or the objects that fell into them. Hawking radiation challenges our understanding of gravity, quantum mechanics, and the fundamental nature of information. It suggests that black holes are not permanent cosmic prisons, but are instead dynamic objects with a finite lifespan. This concept redefines our view of the universe's most extreme objects, showing that even the darkest regions of space are subject to the passage of time and the laws of thermodynamics. The theory of Hawking radiation is a reminder that the cosmos operates under principles that often defy common sense, merging quantum mechanics with general relativity in ways that reveal the universe's complexity and interconnectedness. It suggests that even in the most mysterious corners of space, nature adheres to underlying laws that link the smallest particles to the largest cosmic structures. Quantum gravity. The quest for unification. Quantum gravity is the field of physics that seeks to reconcile general relativity, which describes gravity, with quantum mechanics, which describes the other fundamental forces. Despite their success in explaining the universe at large scales and small scales, respectively, these two theories remain incompatible. General relativity views space-time as a smooth, continuous fabric, while quantum mechanics describes reality in terms of discrete particles and probabilities. Unifying these theories into a single framework is one of the greatest challenges in physics. One of the leading approaches to quantum gravity is string theory, which posits that the fundamental building blocks of reality are not point particles but tiny, vibrating strings. According to string theory, these strings exist in multiple dimensions, and their vibrations correspond to different particles and forces. String theory suggests that gravity can be described in terms of quantum principles, potentially providing a path toward unification. However, the theory requires extraspatial dimensions and remains difficult to test experimentally. Another approach to quantum gravity is loop quantum gravity, (ALCOG), which attempts to quantize spacetime itself. In ELCJEG, spacetime is made up of tiny, discrete units or quanta that form a woven network. This approach does not rely on extra dimensions, but instead suggests that spacetime has a fundamentally granular structure. Loop quantum gravity offers insights into black hole interiors and the nature of the Big Bang, suggesting that spacetime might behave differently under extreme conditions. The quest for quantum gravity has implications for understanding the universe's most extreme environments, such as black holes and the Big Bang. In these situations, both gravity and quantum effects are essential, making it impossible to describe them accurately with either general relativity or quantum mechanics alone. A theory of quantum gravity would provide a complete description of these phenomena, shedding light on the origins of the universe and the nature of singularities. Quantum gravity also raises questions about the nature of space and time. If space-time is quantized, it would mean that space and time themselves are not continuous but exist in discrete chunks. This concept challenges our intuitive understanding of reality and suggests that the fabric of the universe is more complex than it appears. A successful theory of quantum gravity would reshape our view of existence, linking the macroscopic and microscopic realms into a unified whole. The search for quantum gravity is a testament to humanity's drive to understand the cosmos at its deepest level. It represents the pursuit of a theory of everything, a framework that could explain all fundamental forces and particles in a single, elegant equation. Quantum gravity invites us to explore the boundaries of knowledge, seeking answers to questions that lie at the very foundation of reality. Dark flow is an unusual phenomenon in which galaxy clusters appear to be moving in a consistent direction toward a region of the sky at velocities that cannot be explained by the expansion of the universe alone. Discovered in 2008, dark flow suggests that there may be an unknown force or structure beyond the observable universe, exerting a gravitational pull on these clusters. This discovery has led some scientists to propose that massive structures outside our observable universe might be influencing the movement of galaxies within it. One possible explanation for dark flow is that it represents the gravitational influence of a supervoid or supercluster beyond the observable horizon, creating a directional pull. However, because these structures lie outside our observable universe, they cannot be directly detected, making the phenomenon difficult to study. If dark flow is real, it could imply that the universe is not homogeneous on the largest scales, challenging the cosmological principle. The existence of dark flow raises questions about the nature of the universe beyond the cosmic horizon. Some theories suggest that our universe may be part of a larger multiverse, where regions with different physical properties exert a gravitational pull across cosmic boundaries. This idea aligns with the concept of a bubble universe, where each bubble represents a separate universe within a larger multiverse. If true, dark flow could be evidence of our universe's interaction with neighboring universes. Dark flow remains a controversial topic, as alternative explanations, such as statistical anomalies or observational errors, have been proposed. However, if further research confirms its existence, dark flow could reshape our understanding of cosmic structure and the forces at work on the largest scales. It suggests that the observable universe may be part of a much larger, interconnected reality, where distant regions influence each other in ways that defy our current models. The study of dark flow highlights the limitations of our observations, as we are confined to a cosmic bubble beyond which we cannot see. It reminds us that the universe may contain hidden structures and forces that lie beyond our reach, shaping the cosmos in ways we cannot fully comprehend. Dark flow is a reminder that the universe is filled with mysteries, some of which may never be revealed but continue to exert their influence from beyond our horizon. The Goldilocks Zone, the search for habitable planets. The Goldilocks Zone, or habitable zone, refers to the region around a star where conditions are just right for liquid water to exist on a planet's surface, a key factor for the potential for life as we know it. If a planet is too close to its star, it will be too hot, and water will evaporate. If it is too far, it will be too cold, and water will freeze. The habitable zone is where temperatures are just right, providing a favorable environment for life to emerge and evolve. The concept of the Goldilocks zone has guided the search for exoplanets that could harbor life. In recent years, missions like Kepler and TESS have discovered thousands of exoplanets, many of which lie within the habitable zones of their stars. These planets vary widely in size, composition, and atmospheric conditions, offering a diverse array of possibilities for potentially habitable worlds. While liquid water is a crucial ingredient, other factors, such as atmospheric composition, magnetic fields, and geological activity, also play a role in a planet's habitability. The size and type of the host star affect the location and width of the Goldilocks zone. For example, smaller, cooler stars like red dwarfs have habitable zones much closer to the star, while larger, hotter stars have habitable zones farther out. Red dwarfs are particularly intriguing targets because they are the most common type of star in the Milky Way, and their long lifespans provide stable environments for billions of years. However, red dwarfs also emit intense radiation and frequent solar flares, which could strip away a planet's atmosphere and pose challenges for life. The search for habitable planets in the Goldilocks zone also includes studying super-Earths and ocean worlds, planets larger than Earth that may have vast oceans beneath their surfaces. These worlds offer unique environments that could support life, even if they differ significantly from Earth. Additionally, moons orbiting giant planets within the habitable zones, like Europa and Enceladus in our solar system, may also contain subsurface oceans and could be potential habitats for life. The Goldilocks zone is a reminder that life requires specific conditions, but may also be more adaptable than we imagine. As technology advances, the search for habitable planets will continue, driven by the hope that one day we may discover distant worlds where life thrives. The Goldilocks zone represents humanity's quest to find others like us in the vastness of space, seeking connections that transcend our home planet and expand our view of what it means to be alive in the universe. The Fermi Paradox. Where is everybody? The Fermi Paradox addresses a profound question. Given the vast number of stars in our galaxy and the high probability of planets that could support life, why haven't we found any evidence of extraterrestrial civilizations? Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox highlights the apparent contradiction between the high likelihood of alien life and the lack of observable evidence. One possible explanation is the rare Earth hypothesis, which suggests that while microbial life may be common, complex life or intelligent civilizations might be exceedingly rare. According to this hypothesis, Earth's particular conditions, including a stable climate, plate tectonics, a protective magnetic field, and a large moon, may be so rare that intelligent life seldom evolves elsewhere. Another theory, called the Great Filter, proposes that at some stage of development, life encounters a nearly insurmountable barrier, or filter, that prevents it from advancing to a technologically advanced stage. This filter could occur at any point in evolution, from the emergence of life itself to the development of intelligence or technology. Another potential answer to the Fermi paradox is the concept of self-destruction. Civilizations may develop advanced technology only to eventually destroy themselves through warfare, environmental collapse, or other self-inflicted disasters. This idea suggests that civilizations reaching a certain level of technology may face existential risks that limit their lifespan, explaining the absence of detectable extraterrestrial societies. Some researchers suggest that alien civilizations may exist but are choosing not to make contact with us. This concept, known as the zoo hypothesis, posits that advanced extraterrestrials may be observing us from afar without interfering, similar to how we might observe animals in a nature preserve. They may avoid contact to allow our civilization to develop without outside influence, or they may be waiting until humanity reaches a certain level of maturity before initiating contact. The Fermi paradox also raises the possibility that we may not be looking in the right way or with the right technology. It's possible that extraterrestrial civilizations use communication methods we haven't yet discovered or exist in forms that are undetectable by our current instruments. Some propose that advanced civilizations may even transcend physical form, existing as digital consciousness or as forms of energy, making detection challenging with conventional methods. The Anthropocene, humanity's impact on Earth's geological history. The Anthropocene is a proposed geological epoch that marks the significant impact humans have had on Earth's environment, climate, and ecosystems. This new era, which some scientists argue began around the Industrial Revolution, reflects the profound changes humanity has caused in a relatively short time. From altering atmospheric composition to reshaping landscapes, humans have left an indelible mark on the planet, making the Anthropocene a distinct chapter in Earth's history. One of the defining characteristics of the Anthropocene is the dramatic increase in atmospheric carbon dioxide levels due to fossil fuel combustion, deforestation, and industrial processes. This increase has led to global warming, shifting climate patterns, and changes in weather extremes. The effects of climate change are felt worldwide, impacting ecosystems, agriculture, and even human health. Human activities have also contributed to the loss of biodiversity, leading some to refer to the Anthropocene as the sixth mass extinction. Habitat destruction, pollution, and overexploitation of species have resulted in unprecedented rates of extinction. The loss of biodiversity affects ecosystem stability, reducing the resilience of natural systems and diminishing the services they provide to humanity. The Anthropocene has reshaped Earth's physical landscape as well. Urbanization, mining, agriculture, and infrastructure development have transformed vast regions of the planet. Rivers have been dammed, forests cleared, and coastlines altered. The Anthropocene is also marked by a proliferation of artificial materials, such as plastics and concrete, which leave a geological record that future generations will be able to study. Proponents of the Anthropocene epoch argue that human impact is so profound that it should be recognized as a distinct geological period, separate from the Holocene. Some suggest that the Anthropocene began in the mid-20th century, marked by the great acceleration in human activity, including population growth, industrialization, and environmental changes. The presence of radioactive isotopes from nuclear testing is often cited as a potential geological marker. The Anthropocene raises questions about humanity's responsibility toward the planet and the legacy we will leave for future generations. It challenges us to consider how our actions affect Earth's systems and how we can mitigate the impacts of climate change, preserve biodiversity, and work toward sustainable development. The concept of the Anthropocene reminds us that we are not separate from nature but are deeply intertwined with the Earth's processes and cycles. The observable universe and cosmic horizon, the edge of what we can see. The observable universe is the portion of the cosmos from which light has had time to reach us since the beginning of the universe, roughly 13.8 billion years ago. This cosmic horizon marks the farthest distance we can observe, limiting our view of the universe to about 93 billion light-years in diameter. Beyond this horizon, regions of space are expanding faster than light can travel, rendering them permanently beyond our observational reach. The observable universe contains hundreds of billions of galaxies, each with billions of stars, stretching across vast cosmic distances. This immense structure is organized into a web-like pattern, with galaxies and clusters connected by filaments of dark matter, separated by vast cosmic voids. Observing this cosmic structure provides insights into the distribution of matter, the formation of galaxies, and the large-scale dynamics of the universe. One of the most intriguing aspects of the cosmic horizon is its impermanence. As the universe expands, galaxies near the edge of the observable universe will eventually move beyond the horizon, becoming undetectable from Earth. This means that the observable universe is constantly changing, with new regions entering and exiting the visible cosmos as time progresses. In the distant future, the accelerating expansion driven by dark energy may cause even nearby galaxies to drift beyond our reach. The edge of the observable universe invites us to consider what might lie beyond our current view. While we cannot observe beyond the cosmic horizon, some theories suggest that the universe could be infinite, extending far beyond what we can see. Others propose that the universe may have a specific shape or boundary, though current observations suggest a flat, nearly infinite expanse. The cosmic horizon serves as a reminder of the limits of human knowledge and the vastness of the cosmos. It challenges us to accept that there may always be regions of the universe beyond our reach, filled with unknown galaxies, structures, and possibly even alternate realities. The observable universe is a humbling boundary, highlighting both the scale of what we can see and the mysteries that lie beyond. Exoplanets and the search for Earth 2.0. Exoplanets, or planets outside our solar system, represent one of the most exciting frontiers in modern astronomy. Since the first exoplanet discovery in 1992, scientists have confirmed thousands of exoplanets, revealing a staggering diversity of worlds. These planets range from massive gas giants to rocky Earth-like planets, some of which lie in their star's habitable zone, where conditions might be suitable for liquid water and potentially even life. The search for Earth 2.0 is driven by the hope of finding a planet with conditions similar to those on Earth. Such a planet would likely be rocky, similar in size to Earth, and orbiting in the habitable zone of a star. Discovering an Earth analog would have profound implications for our understanding of life in the universe, and could even provide a potential destination for future human exploration. The discovery of exoplanets has led to advancements in methods for detecting and studying distant worlds. The transit method, which observes the slight dimming of a star as a planet crosses in front of it, has been highly successful in identifying exoplanets. The radial velocity method, which measures the wobble of a star caused by the gravitational pull of an orbiting planet, has also yielded numerous discoveries. Newer techniques, such as direct imaging and studying the atmospheres of exoplanets, offer even more detailed information. One of the most promising tools for exoplanet research is the James Webb Space Telescope, JWST, which had capability to analyze exoplanet atmospheres for signs of habitability or even biosignatures. By studying the chemical composition of an exoplanet's atmosphere, scientists can look for elements such as oxygen, methane, and carbon dioxide, which could indicate the presence of life or conditions similar to those on Earth. Exoplanet discoveries continue to challenge our understanding of planetary formation and the diversity of planetary systems. Some exoplanets, known as hot Jupiters, are massive gas giants that orbit very close to their stars, defying previous models of planetary system formation. Other types include super-Earths and mini-Neptunes, which have no direct analogues in our solar system, suggesting that planetary systems can form in a wide variety of configurations. The search for exoplanets and Earth-like worlds is a journey of discovery, expanding our knowledge of the cosmos and fueling our curiosity about life beyond our solar system. Each new exoplanet brings us closer to understanding whether Earth is unique or one of many inhabited worlds. The quest for Earth 2.0 represents humanity's desire to find our place in the universe, seeking connections to worlds that may be like our own and pondering the possibility of life in distant, alien realms. The cosmic web. the universe's hidden structure. The cosmic web is the large-scale structure of the universe, composed of vast filaments of dark matter and galaxies that stretch across hundreds of millions of light years. This intricate network connects clusters of galaxies and forms the skeleton of the cosmos, with massive voids between the filaments where galaxies are sparse or absent. The cosmic web reveals the universe's underlying order, shaped by the gravitational influence of dark matter and the expansion of space. The formation of the cosmic web began after the Big Bang, when slight fluctuations in the density of matter were amplified by gravity. Over billions of years, these fluctuations grew, forming clusters and superclusters of galaxies. Dark matter, which does not interact with light but exerts gravitational influence, played a critical role in this process, creating dense hubs in the web where galaxies formed and connecting them with elongated filaments. Mapping the cosmic web requires studying the distribution of galaxies across the universe. Large surveys, such as the Sloan Digital Sky Survey, have provided detailed maps of the cosmic web, revealing its complex, interconnected structure. These maps allow astronomers to study how galaxies cluster and how dark matter shapes cosmic structure, offering insights into the evolution of the universe on the largest scales. The cosmic web challenges our understanding of space and matter, revealing a universe that is not uniform but organized into a vast, interconnected network. It suggests that galaxies and clusters are not isolated but are part of a larger framework, connected by invisible filaments of dark matter. This structure influences the formation of galaxies, the flow of gas, and the distribution of stars, creating a cosmic ecosystem that spans billions of light years. The study of the cosmic web reveals the hidden structure of the universe, highlighting the role of dark matter in shaping cosmic evolution. It shows us that the universe is not chaotic but has an underlying order, a framework that binds galaxies together and guides their movement. The cosmic web is a reminder that even on the grandest scales, the universe is interconnected, governed by forces and structures that shape the cosmos from the smallest particles to the largest clusters. Neutrinos, the ghost particles of the universe. Neutrinos, often called ghost particles, are incredibly small, nearly massless particles that rarely interact with matter. Produced in enormous quantities by nuclear reactions within stars, supernova explosions, and radioactive decay, neutrinos pass through ordinary matter almost undisturbed. Trillions of neutrinos pass through every square centimeter of your body every second, yet they rarely collide with atoms, making them some of the most elusive particles in the universe. Neutrinos were first proposed in the 1930s by physicist Wolfgang Pauli, who suggested their existence to explain certain energy losses in radioactive decay. They were finally detected in 1956, confirming their existence and marking a breakthrough in particle physics. Since then, neutrino detectors, often located deep underground or under the ocean to shield from other particles, have been built around the world. These detectors capture the rare interactions between neutrinos and atoms, allowing scientists to study these ghostly particles in detail. One of the most intriguing properties of neutrinos is their ability to oscillate or change flavors as they travel through space. There are three types or flavors of neutrinos: electron, muon, and tau. Neutrino oscillation means that a neutrino can switch between these types, a phenomenon that requires neutrinos to have a small but non-zero mass. This discovery challenged the standard model of particle physics, which had previously assumed that neutrinos were massless. Neutrinos play a crucial role in understanding both the microscopic and cosmic scales of the universe. In astrophysics, they serve as messengers from distant, high-energy events, such as supernovae and gamma-ray bursts. Because neutrinos interact so weakly with matter, they can escape from these events and travel across vast distances without being absorbed or deflected, carrying information about the processes occurring in extreme cosmic environments. Studying neutrinos also has implications for understanding the nature of matter and antimatter. Some theories suggest that the behavior of neutrinos could help explain why the universe has more matter than antimatter, a mystery that has puzzled scientists for decades. If neutrinos exhibit certain asymmetries in their behavior, they might provide clues to this imbalance, shedding light on the conditions of the early universe. Neutrinos remind us that the universe is filled with particles that interact in subtle, almost invisible ways. They offer a glimpse into the hidden processes at the heart of stars, galaxies, and cosmic explosions, connecting the smallest particles to the largest structures in the universe. Through the study of neutrinos, we explore the fundamental building blocks of matter, unveiling secrets that lie beyond the reach of ordinary observation. Dark energy and the accelerating universe. Dark energy is the mysterious force that is causing the universe's expansion to accelerate. Discovered in the late 1990s through observations of distant supernovae, dark energy is thought to make up about 68% of the universe's total energy density. Despite its vast influence, the nature of dark energy remains one of the most profound mysteries in cosmology, with scientists unsure whether it is a constant force, an unknown particle, or a property of space itself. The discovery of dark energy challenged the traditional view of gravity as a force that would gradually slow down cosmic expansion. Instead, observations reveal that galaxies are moving apart at an increasing rate, implying that a repulsive force is driving this acceleration. Dark energy's influence grows stronger as the universe expands, suggesting that it may be a fundamental property of space, causing empty regions to expand and accelerating the overall growth of the cosmos. One leading theory for dark energy is the cosmological constant, a term originally introduced by Einstein. In this view, dark energy is a constant energy density that fills space uniformly, exerting a repulsive force that drives expansion. Another possibility is that dark energy is a dynamic field, sometimes called quintessence, that changes over time and space. This field could evolve in ways that affect the universe's expansion differently at different stages of cosmic history. The study of dark energy is crucial for understanding the ultimate fate of the universe. If dark energy remains constant, the universe will continue expanding forever, leading to a big freeze where galaxies drift apart, stars burn out, and the cosmos becomes dark and cold. If dark energy's strength increases over time, it could lead to a big rip, where galaxies, stars, and even atoms are torn apart by an accelerating expansion. Alternatively, if dark energy reverses, it could cause the universe to collapse in a big crunch. Dark energy challenges our understanding of space, time, and the fundamental forces that govern the universe. It suggests that the cosmos is not only expanding but evolving in ways that may lead to outcomes beyond our current understanding. The mystery of dark energy invites us to explore the boundaries of knowledge, seeking answers to questions that could redefine our understanding of the universe's origin, evolution, and fate. Panspermia, the cosmic seed theory. Panspermia is the hypothesis that life on Earth, and possibly elsewhere in the universe, may have originated from microorganisms or chemical compounds that travel through space. According to this theory, life did not necessarily begin on Earth, but may have been seeded here by comets, asteroids, or interstellar dust. Panspermia suggests that life's building blocks are spread throughout the cosmos and could potentially take root on any suitable planet. One form of panspermia, known as directed panspermia, proposes that life may have been intentionally seeded by an advanced civilization. This idea, though speculative, raises intriguing questions about the potential for life to spread between star systems and even galaxies. Alternatively, natural panspermia suggests that microorganisms could survive the harsh conditions of space, hitching rides on meteoroids or comets and eventually landing on planets where they find suitable conditions to thrive. Support for panspermia comes from studies showing that certain types of bacteria and spores can survive extreme conditions, including exposure to radiation, vacuum, and extreme temperatures. These findings suggest that microorganisms could survive a journey through space, protected by rocky material. Some meteorites found on Earth contain amino acids, which are essential building blocks of life, hinting that organic molecules might be common in space. The discovery of organic compounds on comets and in interstellar clouds provides further evidence that life's ingredients are widespread in the universe. Missions like the European Space Agency's Rosetta probe, which studied the comet 67P Churyumov-Gerasimenko, found complex organic molecules on the comet's surface, suggesting that comets could have played a role in delivering life's precursors to early Earth. While panspermia remains a hypothesis, it expands our understanding of life's potential origins. It suggests that life may not be an isolated occurrence but rather a cosmic phenomenon, spread across the universe by natural or intentional means. If panspermia is correct, it implies that life could be far more common than we currently believe, existing on planets and moons throughout the galaxy. Panspermia invites us to view life as a cosmic process, one that transcends planetary boundaries and raises the possibility that we are connected to a larger, interstellar ecosystem. It challenges us to think of Earth as part of a vast network of life, seeded by cosmic forces and potentially sharing kinship with organisms across the galaxy. White holes, theoretical opposites of black holes. White holes are hypothetical objects in space-time that are the theoretical opposites of black holes. While black holes pull in everything, including light, a white hole would eject matter and energy, preventing anything from entering. First proposed as a solution to Einstein's equations of general relativity, white holes have remained purely theoretical, as no observational evidence has yet been found to confirm their existence. According to some interpretations, white holes could be connected to black holes through a wormhole, forming an Einstein-Rosen bridge. In this model, matter that falls into a black hole could theoretically exit through a white hole in another region of space or even another universe. This concept, however, remains speculative as it requires conditions that may not exist in our universe. One possible explanation for white holes is that they are the final stage of black holes. As black holes emit Hawking radiation and lose mass, they might eventually reach a point where they reverse and become white holes. In this scenario, the white hole would emit the remaining mass and energy of the black hole, effectively evaporating in a burst of radiation. This process, however, would take an incredibly long time, potentially longer than the current age of the universe. White holes raise intriguing questions about the nature of space-time and the conservation of information. If black holes trap information, white holes could, in theory, release it, allowing for a balance in the universe's information content. Some physicists have suggested that white holes could play a role in the information paradox of black holes, offering a way for information to escape from black holes without violating the principles of quantum mechanics. While white holes remain speculative, their study offers insights into the possible symmetries of the universe. They challenge our understanding of gravity, thermodynamics, and the structure of space-time, suggesting that the universe may contain hidden connections and phenomena that go beyond our current knowledge. White holes remind us that the universe may hold surprises that challenge our understanding of matter, energy, and causality. They encourage us to explore the boundaries of theoretical physics, seeking answers to questions that lie at the intersection of relativity, quantum mechanics, and the unknown. The cosmos and beyond, a never-ending journey of discovery. As we journey through the vast expanse of space, we are reminded of both the immensity of the cosmos and the limits of human knowledge. Each topic we explored, from the mysteries of dark energy and black holes to the possibilities of life beyond Earth, reflects the incredible diversity and complexity of the universe. These phenomena challenge our understanding and inspire us to seek answers to questions that may lie beyond the reach of current science. The universe is filled with phenomena that defy our comprehension, from ghostly neutrinos that pass through matter unseen to the possibility of multiverses that stretch beyond our observable horizon. We are constantly discovering new elements of cosmic structure, like the cosmic web, where galaxies are interconnected in vast, dark matter filaments, creating a universal network that binds all matter. Every discovery deepens our sense of awe and wonder, reminding us that the more we learn, the more there is left to explore. Human curiosity has driven us to peer into the most distant regions of the universe, analyze the faintest signals, and imagine the most exotic realms of physics. This curiosity fuels not only our scientific endeavors but our sense of connection to the cosmos. In understanding the life cycle of stars, the collision of galaxies, and the dance of gravitational waves, we also uncover the story of our own origins, as all matter, including life itself, emerges from the same cosmic processes. As we look to the future, new missions, telescopes, and experiments will allow us to delve even deeper into these mysteries. Instruments like the James Webb Space Telescope, gravitational wave observatories, and neutrino detectors will continue to unravel the secrets of the universe, bringing us closer to understanding the very fabric of reality. Perhaps one day, we will find evidence of life beyond Earth, uncover the nature of dark energy, or even achieve a unified theory of physics that connects quantum mechanics with the forces of gravity. The universe is not a static entity but an ever-evolving, dynamic expanse filled with forces, phenomena, and mysteries that have yet to be understood. Each discovery opens a new chapter. Each question leads to countless others, And each cosmic phenomenon reminds us of our place in the grand story of the cosmos. This journey of discovery is unending, as there will always be new mysteries on the horizon and deeper realms to explore. In the vastness of space, we are reminded that we are part of something greater than ourselves, a universe that has shaped us, and of which we are all an integral part. As we close this exploration, let's remember that our curiosity is a bridge that connects us to the stars. It's a reminder that while we may be small in the grand scale of the cosmos, our desire to understand, explore, and seek out the unknown is boundless. The universe awaits us, and the journey has only just begun.